Imagine closing your eyes and stepping back in time. Not a few centuries, not even a few million years, but hundreds of millions of years into Earth's past. The continents that you know, North America, Africa, Europe, Asia, Australia, South America, none of them exist yet. Their shapes are missing from the map in your mind. There is no Atlantic Ocean, no Indian Ocean, no familiar outline of countries. Instead, all the land on Earth has gathered together into one enormous piece. This was Pangea. Pangea was a supercontinent, meaning a single landmass made of nearly all the Earth's continents joined together. It formed about 335 million years ago, late in the Paleozoic era, and lasted until about 175 million years ago, when it finally began to break apart. For more than 150 million years, the Earth was dominated by this one vast sweep of land, surrounded by an equally vast ocean called Panthalassa, a word that simply means all sea. Why does this matter? Because the arrangement of continents shapes everything: the climate, the winds, the oceans, and the lives of plants and animals. When the world's land is combined into one, the planet behaves differently than it does today. To understand what Earth was like during Pangea is to imagine an Earth both familiar and alien at once. If you could stand on Pangea, the first thing you would notice is scale. Modern continents end at coastlines. They give you edges and boundaries. Pangea had none. From the center of the land, you could walk for thousands of kilometers in any direction and never see an ocean. You might begin in what we now call North America, travel east into the land that will one day become Europe, and then continue into Asia, all without touching a boat or crossing a sea. Turn south, and you could step into what would one day be Africa and South America, all connected, all part of the same continuous ground. And surrounding it all, Panthalassa stretched outward, so immense that from any shore it might have seemed endless. A single ocean covered nearly 3/4 of the planet, circling Pangea like a ring. On some coasts, the water was shallow and warm, full of reefs and light. In other places, it dropped away into deep blue, an abyss where light quickly faded. For animals, there was no Atlantic barrier, no Pacific divide. Life could spread more freely than it can today, crossing open plains and forests that stretched without interruption across whole future continents. But what was this land actually like? Pangea was not a uniform plain. It was a world of extremes. Close to the ocean, winds carried moisture inland, feeding forests and swamps. Giant trees rose into dense canopies, their roots anchored in thick mud. Rivers snaked across broad valleys, carrying minerals down from mountain ranges and leaving fertile ground where life flourished. Yet the farther you traveled inland, the harsher it became. Rain rarely reached the deep interior. Moisture was lost long before clouds could make the journey across so much land. What remained were vast deserts, bigger than any desert you know today. Red sand stretched for thousands of kilometers, interrupted only by rocky outcrops and occasional rivers that flowed briefly during rare rains before disappearing into the ground. This pattern, wet coasts and dry interiors, was one of the defining features of Pangea. It created sharp contrasts, lush swamps and green belts on the edges, arid wastelands in the middle. Animals and plants had to adapt to whichever region they found themselves in. In the interior, life learned to survive heat, drought, and sudden cold at night. Near the oceans, ecosystems thrived with greater variety, full of amphibians, reptiles, and early forests. The climate of Pangea was shaped not only by its size, but also by its position on the globe. Much of it straddled the equator, where the sun beat down directly, creating tropical belts. Seasonal mega-monsoons swept across parts of the continent, bringing heavy summer rains and long, dry winters. Meanwhile, its northern and southern tips reached into polar regions, where glaciers and ice sheets still clung to the land. Nowhere else in Earth's history has one continent combined such a wide range of climates on a single connected landmass, from frozen south to equatorial heat. Winds, too, were different. On today's Earth, continents break up the movement of air, steering jet streams and redirecting storms. In Pangea's time, winds could travel unbroken for thousands of kilometers. Dust from the deep interior might be carried all the way to coastal forests, where it fed the soil with minerals. Storms could sweep inland without meeting oceans to stop them, their rains fading gradually until only dry winds remained. Even the length of the day was slightly shorter than it is now. Earth rotated faster during the time of Pangea, so a full day lasted about 23.5 hours, not 24. It is a small difference, but one more reminder that this was a different world. The creation of Pangea was itself the product of restless Earth. Our planet's outer shell, the crust, is broken into enormous plates that drift slowly over hotter, softer rock beneath. This movement is called plate tectonics. It happens at only a few centimeters per year, about as fast as your fingernails grow. But given millions of years, it completely reshapes the face of the Earth. Before Pangea, there had been other supercontinents. One was called Rodinia, nearly 1 billion years ago. Later came another, Pannotia, about 600 million years ago. Each formed, broke apart, and scattered its pieces across the globe. Pangea was simply the latest in this cycle, though it is the one we know best. The process was slow but relentless. Small continents collided, folding mountains upward where their edges met. The Appalachians in North America and the Atlas Mountains in North Africa are both scars of those collisions, remnants of the seams that stitched Pangea together. Island chains were swallowed, shallow seas vanished as land pressed against land. By around 335 million years ago, nearly all the continents had fused into a single whole. From above, the map of the Earth would have looked simple, almost empty. One great landmass surrounded by one great ocean. No distant islands to discover, no hidden continents beyond the horizon. The world was unified, and its unity left a mark on everything that lived within it. Life during the time of Pangea was both familiar and strange. By the late Paleozoic and early Mesozoic eras, plants had colonized the land with forests of towering conifers and seed ferns. The air, though drier than ours in some regions, was still alive with insects, though smaller than the giant dragonflies of earlier ages. Amphibians lingered near rivers and swamps. Reptiles spread widely, some beginning to take on traits that hinted at the first true dinosaurs. Along the coasts, shallow seas supported corals, sponges, and ammonites, spiral-shelled relatives of the squid, that drifted through the water in large numbers. It was a time of rebuilding, too. Not long before Pangea reached its full size, Earth had experienced the end Permian extinction, the most devastating extinction event in history. Around 90% of species in the oceans and 70% on land disappeared. The causes were complex. Massive volcanic eruptions in Siberia released huge amounts of carbon dioxide, heating the planet, acidifying the oceans, and choking the atmosphere. For a while, life struggled to recover. Oxygen levels were lower, making survival harder. But over time, new lineages took hold, and Pangea became the stage for the rise of new forms of life. Pangea was not permanent. Even as the forces of tectonics had assembled it, those same forces were already preparing to tear it apart. Beneath the crust, heat continued to build. Faults opened in quiet valleys. Magma pressed upward, filling cracks with dark rock. These were the first signs of the breakup that, millions of years later, would create the Atlantic Ocean and scatter the continents into the shapes we recognize today. But for the time it existed, Pangea defined an age. Its forests and deserts, its rivers and swamps, its endless horizon, all of it shaped evolution and climate in ways we still see today. Fossils of the same species can be found in South America and Africa, in India and Antarctica, because during Pangea's time they were neighbors, connected by land. To walk across Pangea would have been to experience an Earth both boundless and unified. No ocean interrupted your path, no distant land hid beyond the horizon. Everything stretched outward in every direction, all under the same sky. This is Pangea, and to truly understand its story, we must begin at the beginning, with the slow gathering of land, the collisions of continents, and the forces deep beneath the Earth that pulled everything into one. Far beneath our feet, the ground feels solid. We walk on rock. We build our homes on it. We think of it as unshakable. But Earth's outer shell is not a fixed surface. It is broken into enormous slabs like pieces of a cracked eggshell, and those pieces move. Slowly, silently, year after year, they drift across the planet. We call them tectonic plates. The movement is not something you notice in a lifetime. A plate may slide forward just a few centimeters in an entire year, about as fast as your fingernails grow, but when you stretch that movement across millions of years, the results are staggering. Oceans open, oceans close, continents drift together, and continents drift apart. Mountains rise and wear down, landscapes are rebuilt from the inside out. Pangea was the product of this restless Earth. It was not built overnight, and not even in a single geological era. It was the final act in a long play that had been running for hundreds of millions of years. Before Pangea, there had been other supercontinents, Rodinia nearly 1 billion years ago, and later Pannonia, which formed and broke apart around 600 million years ago. Earth has a cycle. Supercontinents form, break, scatter, and reassemble. Pangea was one moment in that cycle, though for us it is the most vivid. In the Paleozoic era, long before dinosaurs walked the Earth, smaller continents and island chains drifted across ancient oceans. They were like rafts on a slow conveyor belt. The largest of these blocks were Laurasia, the landmass that would one day give rise to North America, Europe, and parts of Asia, and Gondwana, which held what would later become South America, Africa, Antarctica, Australia, and India. Between them lay wide oceans, with island arcs scattered across the water like stepping stones. As the plates continued to move, these fragments crept toward each other. The oceans that separated them narrowed, their floors sinking beneath the advancing edges of continents. Where land met land, the collisions were anything but gentle. Rocks folded like cloth pressed under weight. Faults fractured and shifted. Mountains rose where once there had been low plains or shallow seas. The Appalachian Mountains in eastern North America began this way. Long before they were gentle forested ridges, they were sharp, towering peaks created when North America slammed into parts of what are now Europe and Africa. At the same time, the Variska Mountains stretched across Europe, and the Atlas Mountains began to rise in North Africa. These ranges were scars of the collisions that welded the pieces of Pangea together. To imagine what it looked like, picture continents slowly closing in on one another. The ocean in between shrinks year by year. Its basin crumples. Island arcs caught in the middle are swallowed and crushed. Sediments that once rested on an ocean floor are thrust upward into mountain ranges. Volcanic arcs ignite along subduction zones where one plate slides under another, and their lava builds new land on top of old. All of this happened in slow motion. You would not see mountains leap upward in a lifetime, but you would notice earthquakes, eruptions, shifting rivers. To the animals and plants alive then, the earth was not quiet. It shook, it rumbled. It built landscapes under their feet, sometimes tearing apart the places where they lived, sometimes offering new ground to colonize. By around 335 million years ago, after countless collisions, nearly all of Earth's land had fused into one enormous body. The supercontinent Pangea was complete. Its edges stretched from pole to pole. At its center were newly built mountain belts and high plateaus. Around its margins were the scars of oceans that no longer existed, seams where continents had welded together forever. We know this not because anyone saw it, but because the rocks still carry the evidence. Geologists trace matching mountain chains on opposite sides of today's oceans. The Appalachians in North America line up with the Caledonides in Scotland and Scandinavia. Fossils of the same species are found in South America and Africa, in India and Antarctica. Coal deposits and glacial scratches match across continents now divided by entire seas. These are the fingerprints of a world that was once united. The joining of continents also reshaped the climate. When landmasses fuse, they create wide interiors far from the sea. Moisture no longer reaches deep inland, and the result is extreme weather. Summers burned with intense heat. Winters froze with sharp cold. Rainfall patterns shifted, with long dry spells broken by sudden floods. Geologists find proof of these extremes in red beds, layers of iron-rich sandstone formed in hot, arid conditions, spread widely across what was once Pangea. Yet Pangea was not just dry land and mountains. Along its edges, seas still lingered. One of them was the Paleotethys Ocean, squeezed between Gondwana and smaller blocks of land. As collisions closed it off, another ocean began to open. the neotethys, which would later play a major role in Earth's history. These shifting seas were reminders that Earth never stands still. Even as Pangea came together, the seeds of its breakup were already in place. The process of building Pangea released immense energy. Volcanic chains erupted, spreading ash across the skies and pouring lava across landscapes. These eruptions changed the chemistry of the atmosphere and the oceans. They contributed to warming and cooling cycles, to extinctions and recoveries. The joining of continents was not simply the creation of land. It was a global transformation that touched every aspect of the planet. To live on Earth during the birth of Pangea was to witness constant change. In some places, lowlands became mountains within a few million years. Rivers that once flowed gently across plains were dammed by rising ridges, their waters diverted into new valleys. Coastal swamps were uplifted and drained. Forests collapsed in some areas and spread in others. For early reptiles, amphibians, and plants, survival meant adapting to an Earth that was reshaping itself with every generation. And though the world may have seemed unified, it was never calm. Deep within the crust, plates continued to grind and press. Faults slipped, releasing earthquakes. Magma pushed upward, carving new pathways. The supercontinent was vast, but it was not eternal. It was held together by the same restless forces that had built it, forces that would one day undo it. The birth of Pangea was more than a geological event. It was the foundation for the world that followed. By bringing land together, it allowed plants and animals to spread across regions they never could have reached before. Species that had evolved in isolation suddenly shared the same ground. Predators followed prey across new landscapes. Forests stretched across multiple future continents, linking ecosystems in ways that shaped the course of evolution. It also set the stage for crises. The vast interior deserts, the shifting climate, and the stress of constant change challenged life in ways it had never faced before. Some species thrived, others disappeared. The history of life on Pangea is inseparable from the story of its birth. Standing back from this story, you can see the larger rhythm. Continents drift, they gather, they separate. Mountains rise, mountains fall. Pangea was not the first, and it will not be the last. Scientists believe another supercontinent may form in the distant future, hundreds of millions of years from now, as the Atlantic slowly closes again. The Earth is always in motion, but during the time of Pangea, for more than 150 million years, our planet carried one vast land. A land born from fire, pressure, and the slow dance of continents. A land where mountains stitched seams across the crust, where deserts grew under an endless sky, and where the future of life was being quietly prepared. There are moments in Earth's story when change comes slowly, layer by layer, over millions of years. And then there are moments when change strikes so fiercely that life itself seems to collapse. The end of the Permian period was one of those moments. Scientists call it the Permian-Triassic extinction event, but its other name is more haunting, the Great Dying. It happened about 252 million years ago, just as Pangea was reaching its full size. By every measure we have, it was the most catastrophic extinction in Earth's history. Around 90% of all species in the oceans vanished, and more than 70% of species on land were lost. Nearly everything alive was touched by it. The world gasped, and for a time it seemed as if life itself might not recover. What caused such devastation? The Earth offers clues, written in layers of stone, in ancient ash deposits, in chemical fingerprints preserved in fossils. And the story that emerges is one of fire, suffocation, and a planet out of balance. In what is now Siberia, enormous volcanic eruptions tore open the crust. These were not ordinary volcanoes, the kind that throw up a single mountain cone. They were part of something far larger, a large igneous province, a region where magma floods the surface through countless vents and fissures. Over a span of less than 1 million years, a blink in geological time, lava poured out across millions of square kilometers, creating what we call the Siberian Traps. Today, the dark layers of basalt still cover the land, stacked in flows hundreds of meters thick. These eruptions released vast amounts of gases. Carbon dioxide and methane rose into the atmosphere, trapping heat. Sulfur dioxide spewed out too, forming acidic rain that burned ecosystems. The air became heavy with volcanic haze, dimming sunlight in some regions and heating the climate in others. The oceans bore the worst of it. As the atmosphere filled with greenhouse gases, global temperatures climbed. Warmer water holds less oxygen, and circulation patterns slowed. The seas began to stagnate. Life in shallow waters suffocated first. Coral reefs, which had flourished for hundreds of millions of years, collapsed. Ammonites, trilobites, brachiopods, creatures that had endured earlier crises, now dwindled. In deeper waters, microbes that thrived without oxygen took over, releasing toxic gases like hydrogen sulfide. The seas, once full of vibrant life, turned into vast stretches of suffocating darkness. On land, the picture was no less grim. Forests withered under the stress of heat and acid rain. Rivers dried in some regions, flooded unpredictably in others. Insects, usually resilient survivors, suffered a mass decline. Amphibians, already tied to fragile water sources, dwindled. Reptiles survived better, but even many of their lineages disappeared. Entire ecosystems unraveled, each loss echoing through the food web. The numbers alone are staggering, but it is the scale of emptiness that is hardest to imagine. For millions of years before the Great Dying, Earth had been full of sound. Rivers buzzing with insects, oceans alive with schools of fish, forests filled with amphibians calling at night. Then, within a relatively short time, much of that chorus fell silent. Scientists studying ancient soils find evidence of something unusual, a sudden collapse of plant life. Layers rich in spores and pollen are abruptly replaced by layers dominated by fungal remains. It is as if the world turned into a vast compost heap, fungi feeding on the dead and decaying remains of forests. For a time, they were the most visible survivors. And yet, even in this time of devastation, life endured. Some lineages managed to adapt to the new world. A few groups of reptiles survived, their descendants later giving rise to the first dinosaurs. Certain plants held on, their seeds waiting for conditions to improve. Small burrowing animals may have had an advantage, escaping surface extremes. The ocean, too, found pockets where life clung on, tiny communities that would slowly expand as conditions stabilized. The recovery was slow, painfully slow. It took 5 to 10 million years before ecosystems began to rebuild into anything resembling their former richness. During that time, Earth was a quieter place, its landscape stripped down, its oceans struggling back from near silence. But that silence did not last forever. What makes the Great Dying especially important is not just the devastation it caused, but the way it reshaped the path of evolution. By wiping out so many species, it cleared the stage for new ones. Reptiles expanded into roles left vacant by others. Plants spread into open ground once crowded with competitors. And in time, these survivors gave rise to the ecosystems of the Triassic period, the first dinosaurs, and eventually the Age of Giants that followed. The Great Dying also reminds us of Earth's fragility. The same planet that can nurture forests and seas filled with life can, under the right conditions, tip into disaster. Climate, atmosphere, and geology are tied together in ways that can amplify change, creating cascades that reshape the entire biosphere. If you could have walked across Pangea during or after this event, you would have seen landscapes scarred by fire and drought, forests reduced to ash, rivers carrying chemical-laden floods, skies sometimes hazy with volcanic clouds. The air might have felt heavier, the heat pressing against you. Along coasts, the ocean may have smelled strange, carrying the sour tang of gases released from dying waters. The abundance of life that usually fills every corner of Earth would have felt thinner, quieter, as though the planet itself had paused. And yet, even in that silence, seeds of renewal were present. The creatures that survived carried the genetic blueprints for the next age. Tiny ancestors of future lineages were already learning to thrive in niches left behind. Evolution, though slowed, had not stopped. The Great Dying was the deepest crisis life has ever faced. It was not the last extinction, but it was the most severe. By erasing so much, it reshaped everything that came after. And as the Earth settled into its new order, Pangea, still vast, still unified, became the canvas on which new life would paint its story. The great dying left the earth quiet. Oceans had thinned of their reefs, coasts had lost much of their green cover, and the land felt stripped of its familiar chorus of life. In the aftermath, for a time, the planet seemed fragile, as though its living fabric might never fully return. But even in that silence, resilience stirred. Some creatures endured the chaos. Some plants clung to the soil, and from these survivors, new worlds of life began to grow. Recovery did not come quickly. For millions of years after the extinction, Earth was a patchwork of struggling ecosystems. Fossils show that diversity remained low, with only a handful of species holding on in many regions. But the very fact that any life survived meant there was a foundation to build upon. Those that endured did so because they had traits, behaviors, body plans, or sheer luck that let them weather extremes of heat, drought, and poisoned seas. On land, one of the most notable groups of survivors were the lycopods and other primitive plants that could reproduce quickly and spread across barren ground. They acted as pioneers, sending roots into bare soil and stabilizing landscapes scarred by floods and ash. In some places, ferns dominated the early stages of recovery. Their spores spread easily on the wind, allowing them to colonize ground that had been cleared of forests. To look across these regions would have been to see wide carpets of low greenery rather than towering trees, a landscape reset to something simpler. Eventually, sturdier plants followed. Seed ferns, conifers, and ginkgo-like trees returned in scattered patches. Unlike the delicate ferns, these plants grew taller and lived longer, creating new habitats for animals. Their seeds allowed them to survive through difficult seasons, lying dormant in the soil until conditions improved. Slowly, forests began to reclaim parts of Pangea, though they never reached the diversity of earlier times. Among animals, survival took many forms. Some creatures endured by burrowing underground, avoiding the worst of heat and drought. Small therapsids, mammal-like reptiles, left behind fossils that suggest they dug burrows to shelter from extreme temperatures. Inside those hidden chambers, they could escape wild swings of climate and even raise young in relative safety. Their persistence would one day give rise to mammals, but in the Permian's shadow, they were simply survivors, clinging to life in the soil. In the open landscapes above, early reptiles became increasingly important. Their bodies were better suited to dryness than amphibians, whose soft skin and water-bound eggs tied them to ponds and rivers. Reptiles had protective scales and eggs with tough shells that could survive on land. This independence allowed them to spread into regions where amphibians could not follow. Small, fleet-footed reptiles darted across the ground in search of insects or plants, while larger herbivores grazed on the limited vegetation that returned. The oceans, once the center of devastation, also carried survivors. Some lineages of brachiopods, shell-breathing animals that had lived in shallow seas for hundreds of millions of years, managed to cling on. Certain bivalves, ancestors of clams and mussels, proved more adaptable, and in time they expanded into niches left empty by others. Ammonoids, relatives of squid with coiled shells, had been reduced nearly to extinction, yet a few species endured. From that fragile remnant, they would later flourish into spiraled forms that drifted through the Triassic seas. Even in the absence of great coral reefs, marine ecosystems began to rebuild around smaller, sturdier structures. Sponges and algae colonized shallow waters, and microbial mats, simple layers of bacteria and tiny organisms, covered seafloors. These communities may have looked plain compared to the rich coral gardens of earlier times, but they were vital stepping stones in the planet's slow recovery. What makes these survivors remarkable is not only that they lived through crisis, but that their endurance shaped everything that came afterward. By surviving when others could not, they carried forward traits that would define future life. Reptiles, for instance, expanded into new roles on land because amphibians had been weakened. Plants with seeds took on greater importance because spore-based forests had collapsed. And in the oceans, bivalves and ammonoids spread where older reef builders had vanished. The world that emerged was not a return to what had been lost. It was something new, reshaped by absence. The Great Dying had cleared vast ecological space, and those who remained became pioneers of unfamiliar landscapes. Imagine standing on one of Pangea's floodplains a few million years after the extinction. The land is bare in many places, with stretches of cracked soil where vegetation has not yet returned, but here and there you find ferns spreading in low mats. In pockets along a riverbank, seed ferns rise a little taller, offering shade. Small reptiles scurry between them, their tails leaving delicate trails in the dust. Overhead, the sky feels enormous, the silence broken only by the rustle of leaves in the wind or the distant call of an animal. It is not a rich ecosystem, not yet, but it is alive. And in that survival lies possibility. Scientists studying this period often point to a phenomenon called a disaster fauna. This term refers to the small set of species that dominate after a mass extinction. Because so much competition has been cleared away, these few species spread widely, filling spaces that would normally be crowded with many forms of life. In the early Triassic, this meant simple, hardy animals were everywhere. Burrowing therapsids, lizard-like reptiles, a scattering of amphibians, and insect populations that slowly began to recover. Over time, as ecosystems stabilized, new diversity emerged. Reptiles grew larger and more varied. Some took to grazing on the spreading plants. Others became predators, hunting across the open plains. Insects too rebounded, providing food for reptiles and amphibians alike. Slowly, the food webs thickened again, weaving complexity out of the ashes of loss. Recovery was not steady or smooth. Fossil evidence shows that Earth experienced repeated pulses of stress for several million years after the extinction. Climate swings, further volcanic activity, and lingering instability in ocean chemistry meant that life was repeatedly tested. At times, diversity dipped again, as if the Great Dying's shadow stretched long into the Triassic. But with each wave, survivors adapted further, gaining resilience that would anchor ecosystems in the ages to come. For example, early archosaurs, relatives of crocodiles, birds, and dinosaurs, began to appear during this recovery. At first they were small, sharing the land with many other reptiles, but as time went on, they would expand, taking advantage of openings left by extinction. Their presence in the early Triassic is a reminder that survival does not only mean endurance, it can also mean opportunity. The plants that weathered this time were equally transformative. Conifers, with their needle-like leaves and tough seeds, became dominant in many regions. Their ability to withstand dryness and poor soils gave them an advantage. Ginkgo-like trees and cycads also spread, creating new forests that were different from the dense, humid coal swamps of earlier eras. Instead of endless wetlands, Pangea now carried forests of drought-resistant trees, better suited to its vast interior. These forests became the backdrop for the rise of new reptiles and eventually dinosaurs. The slow rebuilding of plant life also influenced the atmosphere. As forests spread, they captured carbon dioxide and released oxygen, slowly rebalancing the planet's air. This interplay between plants and climate was crucial for recovery. Without forests to stabilize soils and regulate gases, ecosystems would have remained fragile. With them, stability returned, step by step. What is striking about these survivors is how ordinary many of them seem. There were no sudden leaps into advanced forms, no miraculous new creatures rising fully formed. Instead, the survivors were simply those with the right tools: hard shells, seeds, burrows, or toughness against drought. They were not spectacular at the time, but they endured, and endurance proved to be the most powerful trait of all. From these modest beginnings, life would flourish again. Within tens of millions of years, dinosaurs would stride across the land, reptiles would rule the seas, and forests would spread from coast to coast. None of that grandeur would have been possible without the quiet persistence of plants and animals that held on in the earliest Triassic. The story of these survivors also reminds us of a deeper truth, that life is both fragile and persistent. Fragile enough to be shattered by global catastrophe, yet persistent enough to return, reshaping itself again and again. The survivors of the Great Dying were not the most spectacular species, but they were the foundation, the ones that kept the thread of life unbroken, allowing the Earth to continue its story. As the Triassic unfolded, that thread would weave into something richer, as forests grew taller and animals became more varied. But in the beginning, it was these quiet survivors, ferns, conifers, small reptiles, burrowers, and scattered marine lineages that carried the planet forward. When we picture a forest today, it often comes with familiar sights: carpets of grass underfoot, blossoms scattering color in spring, bees drifting between flowers, and the soft fragrance of petals opening to the sun. But during the time of Pangea, none of these existed. There was green, yes, and shade, and towering trunks that reached into the sky, but there were no flowers, no grasses, no fruit trees heavy with sweetness. The forests of that world were shaped by older, stranger lineages, plants that thrived long before blossoms evolved. Walking into such a forest would have felt familiar in some ways, yet alien in others. You would have seen conifers, relatives of today's pines and firs, their needles sharp and waxy, their cones hanging heavy with seeds. You would have seen cycads, plants that looked like a cross between palm trees and ferns, their stiff leaves spiraling from stout trunks. And you would have found ginkgo-like trees, broad-leaved with fan-shaped foliage that fluttered in the wind. Together, these plants built entire worlds of green, covering the land in canopies that cast deep shadows on the forest floor. These forests had a quiet order to them. Without flowers to attract pollinators, reproduction worked differently. Conifers relied on the wind to carry their pollen, releasing vast amounts of dust-like grains into the air. Cycads and ginkgos used similar strategies, letting breezes spread their pollen from one tree to another. In the stillness of a Pangean forest, a gust of wind was more than a passing change in weather. It was the lifeline that allowed the next generation of trees to grow. The absence of flowers did not mean the forests were lifeless. On the contrary, they were thriving, full of plants that had adapted to climates ranging from wet coastal regions to the dry interiors. Conifers were especially successful in the arid heart of Pangea. Their needle-like leaves minimized water loss, and their seeds were protected by tough cones, able to endure until the right conditions arrived. In the wetter belts, cycads and seed ferns formed thick groves, their leaves catching the light in broad, leathery arcs. Without grasses to cover the ground, the forest floor looked different from anything we know. Bare soil stretched between tree roots, patches of moss spread across shaded areas. Low ferns grew in clusters, but there were no grassy meadows, no fields waving in the breeze. The animals that grazed in these forests did not nibble on grass. They fed on the tougher leaves of cycads, seed ferns, and young conifers. To our eyes, it might have seemed sparse, but to them it was enough. The lack of flowers also meant that entire groups of modern creatures were absent. There were no bees, no butterflies, no hummingbirds darting through the trees. Pollination was handled not by partnerships between plants and animals, but by chance, pollen grains drifting through the air until they landed on receptive cones. Insects existed, of course, but they were different from the swarms we know today. Dragonflies with wingspans the size of a dinner plate skimmed above rivers. Beetles crawled along bark. Early relatives of cockroaches scuttled in the undergrowth. But they were not yet part of the intricate flower-pollinator dance that would come millions of years later. This gave the forests a different rhythm. Today, blossoms open and close with the sun, and birdsong follows the cycles of nectar and fruit. In Pangea's forests, the cycles were slower, quieter, more dependent on season and wind than on bright displays of color. It was a world painted in shades of green and brown, with only subtle shifts marking the passage of time. Despite their simplicity, these forests were essential to life's recovery after the Great Dying. They stabilized soils, capturing sediments that might otherwise have washed away. Their roots held the ground in place after storms. Their leaves recycled carbon dioxide into oxygen, slowly balancing the air. They created habitats for animals, from reptiles that basked on fallen logs to amphibians that sheltered near streams. Without these plants, the rebuilding of ecosystems would have been impossible. Among the most remarkable were the cycads. Today, they survive mostly in tropical and subtropical pockets, but in Pangea, they were widespread. With thick trunks, tough leaves, and slow growth, they could withstand harsh conditions. Their seeds, large and nutrient-rich, provided food for herbivores. Some cycads even formed partnerships with microbes in their roots, allowing them to capture nitrogen from the soil, an advantage in nutrient-poor environments. To step into a cycad grove during the Triassic would have been to see a plant community built on patience and persistence, each trunk a monument to survival. The ginkgos were equally distinctive. Though only a single species of ginkgo remains alive today, in Pangea they were diverse, spreading fan-shaped leaves across wide territory. Their unique foliage captured sunlight efficiently, and their seeds, though not fruits in the modern sense, carried energy that animals may have eaten and dispersed. In the wind, their leaves trembled with a soft flutter, filling the air with a gentle rustle that would have been one of the defining sounds of these forests. For animals, these forests were both shelter and food source. Small reptiles hunted among the roots, darting after insects. Larger herbivores browsed on the leaves, adapting to chew tough plant matter. Early therapsids, those mammal-like creatures that had survived the Great Dying, may have sheltered in the shade, resting during the hottest parts of the day. Streams that ran through the forests offered water and breeding grounds for amphibians, which clung to existence despite their decline. The structure of these forests also shaped the land itself. Without flowers and fruits, animal diets were narrower, focusing mainly on leaves, spores, and seeds. This influenced how herbivores grew and behaved. Instead of grazing like modern deer or cattle, many early reptiles browsed slowly, processing fibrous leaves with teeth adapted for grinding. Their feeding helped spread plant material, cycling nutrients back into the soil. Predators, in turn, followed these grazers, weaving the first fragile food webs of the Triassic landscapes. One striking feature of these forests was their resilience. They could endure droughts, storms, and poor soils in ways that older coal swamp ecosystems had not. The lush, humid forests of the Carboniferous had collapsed during the Great Dying, unable to survive new extremes of climate. But conifers, cycads, and ginkgos were tougher. They were built for scarcity, for dryness, for unpredictability. This toughness allowed them to dominate Pangea for tens of millions of years, until the later rise of flowering plants challenged their reign. In many ways, the forests of Pangea represent a halfway point in Earth's botanical story. They were more advanced than the spore-driven swamps of earlier ages, but not yet as complex as the flowering forests that would come later. They were landscapes in transition, caught between ancient lineages and future innovations. And in their long reign, they shaped the world that animals inhabited, providing the framework for ecosystems to expand. Imagine walking through one of these forests during the Triassic dawn. The air is warm and dry, scented with resin from conifer bark. Underfoot, the soil is bare, interrupted by patches of moss and ferns. Above, cones hang from branches, releasing pollen into the wind. Dragonflies glide through shafts of light, their wings catching the sun. In the distance, a reptile shifts among the cycads, its movements cautious, its eyes scanning for predators. There is a sense of stillness, but not emptiness. Life is here, steady and persistent, unfolding at its own pace. These are forests that do not bloom, but endure. Scientists studying fossil leaves from this time can trace climate changes written in their shapes. The thickness of conifer needles, the stomata on ginkgo leaves, the patterns of growth rings, all reveal how these plants adapted to shifting conditions. They tell us of droughts, of seasonal floods, of steady resilience. In petrified forests, trunks turned to stone still stand, silent witnesses to an age when plants without flowers ruled the land. The absence of flowers also delayed the appearance of certain animals. Pollinators like bees did not yet exist, and neither did fruit-eating birds or mammals. This meant that many of the intricate co-evolutionary dances we see today, plants shaping animals, animals shaping plants, had not yet begun. The ecosystems of Pangea were simpler in that sense. Yet within that simplicity lay the foundation for everything to come. As time moved forward through the Triassic, these forests became the backdrop for the rise of new creatures. Early dinosaurs walked beneath their canopies, reptiles hunted in their shade, rivers carried their fallen leaves across plains, depositing them in sediments that would one day fossilize. And when volcanic eruptions or climatic swings challenged them, the forests endured, regrowing after each setback. These were not forests of abundance in the way we know them now, with blossoms and fruits bursting each season. They were forests of endurance, of quiet strength, of patience stretched across millions of years. They carried the earth through a time of rebuilding, bridging the gap between destruction and renewal. After the Great Dying, Earth felt quieter than before. The forests were rebuilding, their canopies filled with conifers and cycads, but the air lacked the familiar chorus we might expect from a living world. No birds sang because birds did not yet exist. Mammals were still only small, quiet creatures hidden in burrows. Even the wind, carrying pollen through the trees, seemed to speak louder than the animals that moved below. And yet, out of that stillness, the first small voices began to rise. They came not in thunderous roars or massive footsteps, but in delicate tones, chirps, buzzes, and the soft croaks of creatures testing their calls for the first time. It was the age when insects regained their place in the world, and when the earliest frogs began to leap into being. In their smallness lay a new kind of presence. They did not dominate the landscape, but they gave it sound, and sound was life. Insects had already existed long before Pangea, but they too had been devastated by the Great Dying. Before the extinction, the Carboniferous swamps had been full of giants, dragonflies with wings spanning nearly a meter, millipedes that stretched as long as a human is tall, and cockroach-like insects in staggering numbers. That age had ended. Oxygen levels had dropped, and many of those giants disappeared forever. But insects as a group proved impossible to erase. Their small bodies, short life cycles, and ability to adapt to changing conditions made them some of the most resilient creatures on Earth. By the early Triassic, insects had returned in force. Beetles, one of the most enduring groups in history, left fossils in Pangea's sediments. They fed on decaying plant matter, recycling nutrients back into the soil. Dragonflies, though smaller than their Carboniferous ancestors, still skimmed above rivers, their transparent wings glinting in the sun. Grasshoppers and crickets began to appear, their legs designed for leaping, their sounds beginning to fill the air. For the first time after silence, nights in Pangea would have carried a different rhythm. Imagine lying on the forest floor, looking up at a canopy of cycads. The day heat fades, the shadows stretch, and then you hear it. The high-pitched stridulation of an insect rubbing its legs together, creating a steady pulse. Soon others join in, overlapping into a texture of sound. It is not the birdsong we know today, but it is a chorus nonetheless, a reminder that life is recovering. The mechanics of insect sound are fascinating in their simplicity. Without vocal cords, insects use their bodies themselves to create noise. Crickets produce chirps by scraping their wings together. Grasshoppers rub their legs against ridged parts of their wings. Cicadas, though not yet common in the early Triassic, would later evolve special membranes that vibrated like drums. Each sound is a signal, a call to attract mates, a way to claim space, or sometimes a warning. Even in Pangea, these tiny messages must have echoed through the undergrowth, subtle but constant. Insects also played another critical role. They were among the first creatures to re-establish pollination, even before flowers evolved. Though the forests of Pangea relied mainly on the wind to spread pollen, some insects began to interact with cones and spores, carrying grains from place to place. It was a primitive relationship, far simpler than the elaborate partnerships of bees and blossoms that would come later. But even this early connection hinted at the roles insects would grow into, bridges between plants and the wider ecosystem. If insects were the first notes of Pangea's recovery, frogs were among the first voices to truly break the silence. The earliest frogs appeared in the Triassic, emerging from the surviving lineages of amphibians. Unlike the bulky, salamander-like creatures of the Permian, these new forms were smaller, lighter, and more agile. They had long hind legs built for leaping, and their bodies were adapted for both land and water. Most importantly, they had voices. The call of a frog is created by pushing air over vocal cords, often amplified by a throat sac. Even the earliest frogs likely had the ability to make short, resonant sounds, perhaps simple croaks, rather than the complex choruses of modern rainforests. To hear one across a Triassic swamp would have been a sign of renewal. Where frogs call, there is water. Where there is water, life clusters, plants, insects, and the animals that feed on them. Early frogs were not widespread at first. Their fossils are rare, suggesting they lived in pockets where conditions allowed. Shallow ponds, floodplains, and shaded riverbanks would have been their domains. In those places, their gentle croaks cut through the quiet, announcing both their survival and their connection to a lineage that would stretch unbroken into the present day. The emergence of frogs also meant something important for the structure of ecosystems. Amphibians had suffered terribly in the Great Dying because of their dependence on water. But frogs represented a new strategy. Their strong legs let them move quickly between habitats, escaping danger. Their permeable skin still tied them to moist environments, but their agility allowed them to exploit those environments more effectively. They ate insects, keeping populations balanced, and in turn became prey for small reptiles. Even in small numbers, they reconnected strands of the food web. It is worth pausing to imagine how transformative this must have felt on a sensory level. For millions of years after the extinction, nights may have been almost completely silent, save for the wind in the trees. Then came the first insect songs, adding rhythm to the darkness. And then, layered on top, the occasional croak of a frog, low and resonant. These sounds were modest, but they marked a return to complexity. The living world is not only about sight, it is about sound, and Pangea was finding its voice again. Beyond their songs, insects and frogs brought motion to the recovering landscapes. Dragonflies darted across rivers, their wings shimmering like fragments of glass. Beetles burrowed into fallen logs, leaving trails of tunnels. Crickets jumped from leaf to leaf, vanishing in bursts of energy. Frogs leapt suddenly from riverbanks into water, their splash the loudest sound for meters around. Each small act added vibrancy to places that had once felt barren. The fossil record even preserves some of these moments. Impressions of insect wings, delicate and veined, show us how fragile yet enduring they were. Frog bones, tiny and lightweight, are found in sediments that once were ponds. Together, they remind us that even the smallest creatures leave traces strong enough to last for hundreds of millions of years. The significance of these first small voices goes beyond their presence. They show how recovery works in nature. After a catastrophe, it is not the largest or most powerful creatures that return first. It is the small ones, insects, frogs, burrowers, plants with tough seeds. Their adaptability allows them to find niches, to spread, to multiply. They do not need abundance to survive, only opportunity, and as they take root, they prepare the way for larger animals to follow. In this sense, the insects and frogs of Pangea were the foundation of the new ecosystems. Insects broke down plant matter, returning nutrients to the soil. Frogs kept insect populations in check, creating balance. Reptiles fed on both, weaving themselves into the chain. Each connection added stability, step by step, until ecosystems could sustain more diversity. If you could walk into one of these early Triassic wetlands, the scene would feel hushed but alive. The water is calm, edged by cycads and horsetail plants. A dragonfly lands on a stalk, wings quivering. From the shadows you hear a faint trill, the sound of an insect marking its presence. Then, almost unexpectedly, a short croak rises from the water's edge, followed by a ripple on the surface. It is not a loud sound, not a chorus, but it is enough. You would know in that moment that life has found its voice again. Over millions of years, these voices grew in number and variety. Insects diversified into countless forms, filling nearly every possible niche on land and in fresh water. Frogs expanded into wider habitats, their calls evolving into more complex songs. Together they gave Earth back its soundtrack, the hum and croak and rustle that makes a world feel inhabited. The forests of Pangea, though flowerless, were no longer silent. Between the rustle of ginkgo leaves, the buzz of insects, and the croak of frogs, they had become soundscapes. To us, these noises might have seemed faint compared to modern rainforests, but in their time, they were a triumph. They were proof that recovery was not only possible, but already happening. The Earth, which had nearly gone silent, was learning to sing again, quietly at first, but with growing confidence. If you stood on the shores of Pangea and looked outward, you would not see another continent across the water. There were no distant coastlines, no chains of islands scattered on the horizon. There was only water, stretching farther than the eye could ever follow. This was Panthalassa, the one great ocean that surrounded the united landmass of Pangea, covering nearly 3/4 of the Earth's surface. To us today, the Pacific seems vast and endless, but Panthalassa was larger still, a single world sea without boundaries. The scale of it is difficult to grasp. Modern oceans are broken up by continents, their currents shaped by land masses that interrupt their flow. But Panthalassa was nearly uninterrupted, a sheet of salt water encircling the planet. Its surface glittered under the Triassic sun, while beneath, unseen currents carried warmth from the equator toward the poles and brought cold water back again. In this watery world, life had to adapt, to openness, to distance, to a sense of vastness unlike anything we know today. For creatures living in its shallows, Panthalassa was both a home and a challenge. Along Pangea's coasts, reefs began to rebuild after the devastation of the Great Dying. The reefs of earlier ages, those made by corals and sponges, had collapsed, but now new builders emerged. Instead of modern coral, these reefs were often formed by sponges and by algae that secreted hard skeletons. They created knotted frameworks where fish could dart and shelter, where crustaceans could hide, and where mollusks could attach themselves. These structures may have been smaller and less colorful than the reefs we know today, but they were vital sanctuaries of life. One of the most iconic creatures of these seas were the ammonites. Their shells, coiled in perfect spirals, they drifted through the water like floating ornaments. Ammonites were relatives of modern squids and octopuses, but unlike their soft-bodied cousins, they carried their homes with them. Each chambered shell provided buoyancy, allowing the animal inside to control its depth in the water. They were both predators and prey, catching small fish and plankton with their tentacles, while themselves hunted by larger reptiles that would later dominate the seas. Ammonites became so abundant and widespread that today their fossils are found on nearly every continent, a reminder of just how successful they were in Panthalassa's expanse. The open waters of Panthalassa were not uniform. Near the coasts, sunlight filtered down through shallow seas, feeding plankton and creating food webs that supported fish, ammonites, and early marine reptiles. Farther from land, the waters grew darker, emptier, more difficult to inhabit. Few creatures could thrive in the vast mid-ocean, where food was scarce and distances immense. To cross that emptiness would have been perilous, but along the continental margins, life flourished in growing variety. Panthalassa was also a restless place. With so much water unbroken by continents, winds could sweep across its surface for thousands of kilometers, raising enormous swells. Storms that gathered near the tropics could travel unimpeded, their waves hammering against Pangea's coastlines. Seasonal changes created monsoons that spilled into the ocean, carrying sediments and nutrients from the rivers of the supercontinent. Those sediments fed the coastal ecosystems, while also painting the waters red and brown near river mouths. For all its immensity, Panthalassa was not silent. The water itself carried sound more efficiently than air, and the ocean would have been alive with the subtle clicks, snaps, and vibrations of its inhabitants. Ammonites moved with gentle propulsion, their tentacles fluttering. Schools of fish darted in coordinated flashes, their scales reflecting beams of light. Early marine reptiles sliced through the water, their tails sweeping behind them. Even the reefs produced sound. Snapping shrimp, clattering, shells scraping, water hissing as it moved through coral-like structures. For any creature drifting in the mid-water, the ocean was less an empty void than a network of faint, continuous signals, guiding them through the vastness. The chemistry of the sea also shaped the creatures within it. After the Great Dying, Panthalassa's waters had been depleted of oxygen in many regions, suffocating life. Recovery took time. Slowly, circulation patterns improved, bringing oxygen back into deeper layers. Life clustered where conditions were best, in shallow seas or near upwellings where nutrients rose from the depths. These were the oases of Panthalassa, patches of abundance in a sea of challenges. In these places, ecosystems rebounded, forming the foundations for the diversity that would later spread across the globe. Some of the earliest fish to thrive here were relatives of modern bony fish. Their streamlined bodies allowed them to navigate open waters more effectively than earlier armored fish. Cartilaginous fish, the ancestors of sharks and rays, also survived and began to diversify again. Though smaller than the giants of later ages, these fish were agile hunters, preying on invertebrates and young reptiles. The ocean food web was rebuilding from the bottom up. Plankton fed small filter feeders which fed larger fish, which in turn supported ammonites and marine reptiles. One of the striking features of Panthalassa was its role as a global connector. With no barriers of land, currents carried organisms across immense distances. Ammonites, for example, spread their species worldwide, so that the same forms appear in rocks on what are now separate continents. This wide distribution is one reason ammonite fossils are so valuable to geologists. They provide a timeline, a way to date layers of rock based on which species of ammonite they contain. In their time, though, these animals were simply survivors of a changing world, navigating the open sea with quiet persistence. The reefs, too, served as hubs of diversity. Though not as expansive as modern coral reefs, they were still bustling with life. Sponges filtered water for food. Crinoids, relatives of sea stars, waved feathery arms to capture passing particles. Small crustaceans scuttled over surfaces, while fish hid in crevices. For predators, reefs offered rich hunting grounds. For prey, they provided shelter. These ecosystems were the nurseries of Panthalassa, places where the balance of survival played out on a miniature stage. The ocean also left its mark on the land. Moisture carried from Panthalassa fed the coastal climates of Pangea, influencing forests and rivers. Salt spray coated rocky shores, leaving white crusts where waves broke. Fossil evidence suggests that tides shaped estuaries along Pangea's margins, where fresh and salt water mixed in shifting patterns. These estuaries were critical zones, supporting life adapted to both conditions. Amphibians, reptiles, and insects from the land mingled with fish and mollusks from the sea, creating transitions between worlds. At night, under a sky free of city lights, Panthalassa would have reflected the stars. The Milky Way stretched across its surface, mirrored in dark waters. For early reptiles swimming near the surface, or for insects skimming along coastal shallows, the divide between sea and sky might have blurred. It was a world both vast and intimate, where horizons curved endlessly, and yet every ripple carried life. What makes Panthalassa especially fascinating is that it reminds us how much of Earth is shaped by the sea. Though it seems like an empty backdrop, it was the stage on which life rebuilt itself after near collapse. The Great Dying had nearly erased ocean ecosystems, but Panthalassa became the crucible of renewal. From its shallows came ammonites, fish, and the first great marine reptiles. From its reefs came the complexity needed to support wider food webs, and from its currents came the mixing that spread species across the globe. To imagine standing on Pangea's coast and gazing into Panthalassa is to imagine a world defined by openness. No matter where you looked, water stretched outward without end. Beneath the waves, creatures tested new forms and strategies, slowly writing the future of life in salt and motion. The land may have been the heart of Pangea, but the ocean was its skin, wrapping the supercontinent in a ceaseless embrace. The ocean that wrapped around Pangea was more than empty water. Within Panthalassa, power and grace shaped new rulers of the sea. Fish darted in schools, ammonites drifted with their spiral shells, but something larger was stirring. From the lineages of land reptiles came pioneers that left the shore behind and committed themselves fully to the water. They would become the great swimmers of the Triassic seas, ichthyosaurs, nothosaurs, and a variety of marine reptiles that turned the vast ocean into their hunting ground. Imagine looking down through clear coastal waters. At first you see familiar forms, fish, mollusks, corals. Then a shadow passes below, long, sleek, and fast, An animal surges upward and slices through the water with the precision of a modern dolphin. This is an ichthyosaur, one of the most remarkable creatures ever to evolve. Though it descended from land reptiles, its body had transformed into a streamlined shape, perfectly suited for swimming. Its limbs had become flippers, its tail moved side to side like a fish, and its snout stretched forward into a long point, filled with sharp teeth for catching prey. In the early Triassic, ichthyosaurs were still developing their form, but even then they were already among the fastest predators in the ocean. Their name means fish lizard, and that is fitting. They were reptiles, but they looked more like dolphins or tuna. Over millions of years, they would grow into giants, some as long as a bus, dominating Panthalassa's open waters. Yet even the smaller species, barely a few meters long, were agile hunters. They fed on fish and squid-like creatures, snapping them up with quick movements and swallowing them whole. Fossils show their big eyes, some of the largest ever found in any animal, adapted for seeing in the dim light of deeper waters. With vision like that, they could dive far below the surface, chasing prey where sunlight faded into darkness. Not all marine reptiles were built for the open ocean. Along the coastlines and shallow seas, another group ruled. These were the gnathosaurs, slimmer and more serpentine than ichthyosaurs. Their bodies were long, their necks flexible, and their limbs less specialized. Unlike ichthyosaurs, they still needed to haul themselves onto land now and then, perhaps to rest or lay eggs. They swam with sweeping strokes of their webbed feet and tails, gliding through lagoons and estuaries. Fossils of gnathosaurs show narrow skulls lined with teeth that interlocked like the tines of a comb, perfect for catching slippery fish. If ichthyosaurs were the sprinters of the open sea, gnathosaurs were the ambushers of the coast, waiting in quiet shallows before striking. The presence of these reptiles tells us something important about the Triassic oceans. After the Great Dying, ecological space was empty. Marine reptiles filled niches that had been left open, adapting rapidly to new opportunities. Some became streamlined hunters, some lurked in lagoons, and others experimented with different shapes and strategies. Diversity returned step by step, and with it came balance. Panthalassa was no longer just a sea of fish and invertebrates. It now held predators at the top of the chain, animals large enough to influence everything below. Picture a Triassic bay at dusk. The surface glows with the last light of the sun. Near the shallows, gnathosaurs float just beneath the water, their eyes scanning for movement. A school of small fish passes, and with a sudden lunge, one disappears into a reptilian jaw. Out in deeper water, an ichthyosaur bursts upward, scattering waves as it leaps briefly into the air before plunging back down. These were not mindless monsters, but elegant survivors, each adapted to a part of the ocean. Their presence gave rhythm to the seas, turning calm waters into theaters of pursuit and escape. Fossils give us intimate glimpses of their lives. Some ichthyosaur skeletons contain the remains of unborn young, showing that they gave birth in the water instead of laying eggs on land. This adaptation freed them from ever needing to return to shore, making them fully marine. Others contain clusters of fish bones in the stomach, a snapshot of their last meal. Tracks and drag marks near ancient coastlines suggest where gnathosaurs may have pulled themselves ashore. Through these traces, we can reconstruct not only their bodies, but their behaviors. The evolution of these reptiles also reflects the resilience of life. From land reptiles struggling to recover after extinction came new shapes and lifestyles. It is a reminder that Earth does not simply replace what is lost, it invents anew. Where once there were giant amphibians dominating rivers, there were now sleek ichthyosaurs racing across the seas. Where Permian predators had ruled swamps, Triassic gnathosaurs explored lagoons. Each extinction opens a door, and each survivor finds a way through it. Other marine reptiles shared Panthalassa as well. Placodonts, with stocky bodies and crushing teeth, fed on shellfish along the seafloor. Some even developed armor-like shells on their backs, giving them a turtle-like appearance. Their role was different again. Specialists in cracking the hard defenses of clams and in reefs and coastal shallows, they shuffled slowly, powerful jaws grinding through shells that few other animals could eat. Each group carved out its niche, and together they made the Triassic seas far richer than they had been in the first years after the Great Dying. The rise of these reptiles had larger consequences too. By hunting fish, squid, and ammonites, they shaped populations lower in the food chain. Their presence kept ecosystems from collapsing into imbalance. They also connected distant parts of Panthalassa. An ichthyosaur could travel great distances, moving between regions and spreading energy from one ecosystem to another. Life was no longer confined to small, isolated patches. It was becoming global again. It is striking to imagine the variety of shapes in those seas. A placodont, with its heavy armor grazing near the bottom, a nothosaur twisting gracefully among reeds, an ichthyosaur darting past in a blur of speed. Each movement reflected millions of years of trial and error, of evolution sculpting bodies for survival. None of these forms were inevitable. They were experiments, and some would last for tens of millions of years, while others would vanish as quickly as they appeared. But in their time, they were the undisputed giants of the water. At night, the ocean around them would have felt vast and still. The moon reflected on the waves, schools of fish shimmered below, and the great reptiles patrolled in silence. Sound traveled differently here, carrying the splash of a tail or the rush of a dive over great distances. For ammonites drifting near the surface, such sounds were warnings. For fish, they were signals to scatter. For the reptiles themselves, they were part of the rhythm of hunting. The legacy of these Triassic giants is preserved today in stone. Fossils of ichthyosaurs are found high in the Alps, where ocean floors were later lifted into mountains. Nothosaurs appear in what are now deserts, far from any sea. Placodonts are known from the rocks of Europe and China. Each fossil is a reminder that where we now see dry land, once there was water filled with reptiles that swam as confidently as any dolphin or whale today. Their story also shows how life transitions. In the Triassic, mammals were still tiny, birds had not yet taken flight, and dinosaurs were only beginning to rise. Yet in the oceans, reptiles had already claimed dominance. They were the first to take the role that whales would later hold, turning the seas into arenas of giant hunters. Without them, the balance of the Triassic world would have been very different. And so, as Pangea's forests grew on land, and insects and frogs added their voices to the night, the oceans had their own rulers, not silent but swift, not fragile but strong. They were the embodiment of adaptation, proof that even in the wake of catastrophe, life finds ways to fill every space. In Panthalassa, that meant reptiles reshaping themselves into swimmers and claiming the greatest stage on Earth, the endless sea that surrounded one world of land. When people imagine dinosaurs, they often picture towering giants like Brachiosaurus or the fierce jaws of Tyrannosaurus rex. But those icons belong to a later age. In the Triassic, when Pangea still held the continents as one, dinosaurs were just beginning their story, and they did not yet rule the land. They were small, swift, and in many ways fragile compared to what they would later become. Their world was still filled with other reptiles competing for dominance, and yet in those early forms, the blueprint of future greatness was already present. To see one of these first dinosaurs would not have felt like witnessing a monster, but more like glimpsing a creature on the edge of transformation, something caught between what came before and what was still to come. Among the earliest of these pioneers was Chylophysis, a slender predator no taller than a person and lighter than most large dogs. It ran on two legs, balancing with a long tail, its body built for speed rather than strength. Its teeth were sharp, its jaws narrow, perfect for seizing small prey like insects, amphibians, and early reptiles that shared the floodplains. Fossil beds in what is now New Mexico have revealed entire groups of Chylophyses preserved together, suggesting that they may have moved in packs, weaving through forests and river valleys in restless pursuit of food. Their skeletons tell us of agility, of quick movements, of eyes that scanned constantly for the flicker of motion. They were not yet dominant, but they were survivors, filling niches with quiet efficiency. While Chylophysis represented speed and hunting skill, another early dinosaur shows us the first steps toward the giants that would one day tower over landscapes. This was Plateosaurus, a bulky herbivore that could grow up to 9 meters long. It stood on two legs when it wanted to reach higher branches, but could also walk on all fours as it grazed across plains. Its long neck and powerful jaws allowed it to feed on conifers and cycads, stripping leaves and swallowing them whole. Fossils of Plateosaurus are found across Europe, showing that it was one of the most widespread dinosaurs of its time. Unlike the nimble Coelophysis, Plateosaurus relied on size and strength. Its body massive compared to most other Triassic animals. It was not yet the towering sauropod of later ages, but in its frame we see the first outlines of the colossal plant eaters that would dominate the Jurassic. These two dinosaurs, so different in shape and strategy, mark the early split in dinosaur evolution. On one side, small and agile carnivores testing speed and precision. On the other, larger herbivores learning to exploit plants on a scale no creature had attempted before. From these beginnings would come the great diversity of later ages, but in the Triassic, they remained only a small part of the landscape. Their rise was not yet assured. They lived among other reptile groups that held power in numbers and variety. Crocodile-like relatives, called pseudosuchians, were common across Pangea, filling roles as hunters in rivers and on land. Mammal-like reptiles still lingered in places, holding on after their near destruction in the Great Dying. Early turtles crept along riverbanks, armored and cautious. In such a world, dinosaurs were only one thread in a complex tapestry, not yet the dominant color. What allowed them to endure and eventually thrive was not overwhelming strength, but adaptability. Their upright stance, with legs positioned directly beneath the body, rather than splayed to the sides, gave them stamina and efficiency in movement. They could travel long distances, cover ground quickly, and use less energy doing so. Their eggs, laid in simple nests, could hatch in large numbers, giving them resilience when times were harsh. And their variety of forms, some small, some large, some hunters, some grazers, meant they could exploit different environments at once. These advantages were subtle in the Triassic, but they planted seeds for future dominance. If you were to walk across one of Pangea's floodplains in this era, you might first hear the buzzing of insects and the croak of frogs, then see small reptiles skittering through the undergrowth. In the distance, Plateosaurus herds move slowly, their heads dipping and rising as they strip foliage. Suddenly, movement breaks the rhythm. A pack of Coelophysis races by, their tails straight, their bodies weaving in unison as they chase a smaller reptile toward the water's edge. Dust rises under their feet, the scene brief but intense, over in moments. This was the beginning of the dinosaur world, not yet dominant, but already shaping the drama of life. And other remarkable thread of this story belongs to the sky. Though birds were far in the future, the first flying reptiles had already taken to the air. These were the pterosaurs, cousins of dinosaurs rather than dinosaurs themselves, but they shared the same evolutionary tree. With wings made of skin stretched over elongated fingers, they glided above coastlines and rivers, catching insects and small prey. Some were no bigger than sparrows, fragile and light, their wings casting shadows over the sand. In them we see the first experiment in vertebrate flight, a step that would eventually lead to birds but began here in the Triassic skies above Pangea. The presence of pterosaurs alongside early dinosaurs adds another dimension to this world. On the ground, swift hunters and sturdy grazers shaped life. In the air, delicate gliders expanded the range of possibility. Together they show how quickly ecosystems diversified once stability returned after the Great Dying. Recovery was no longer about survival alone. It was about innovation, about testing new ways to live. The fossil record provides vivid details of these creatures. Plateosaurus bones are so abundant in some areas that entire quarries are filled with them, suggesting mass deaths, perhaps from drought or flooding, that preserved whole herds at once. Coelophysis fossils found with smaller bones inside hint at cannibalism or opportunistic feeding. Pterosaur impressions capture even the delicate structure of wings, showing how fine and precise their membranes were. Each fossil is a frozen glimpse of life in motion, giving us not just shapes, but stories. The rise of early dinosaurs also coincided with dramatic landscapes. The surface of Pangea was restless, split by rift valleys and scarred by volcanic fields. Rivers wandered across wide plains, leaving behind layers of red sediment that are still visible today. Forests of conifers stood tall, while cycads and ginkgo trees spread beneath them. In this setting, dinosaurs carved out their beginnings, their movements traced in the mud and later turned to stone. Footprints of Coelophysis, three-toed and delicate, still mark the rocks of the American Southwest. Plateosaurus tracks stride across ancient floodplains in Europe. To see these prints is to stand where they once ran, to follow their steps across 200 million years of history. It is worth remembering that these animals were not destined to succeed. At several points in the Triassic, environmental pressures could have ended their story before it truly began. Climate shifts, volcanic eruptions, and competition threatened them, but each time they endured, adapting just enough to hold on. By the close of the Triassic, their resilience would pay off, and when another extinction struck at the end of the period, it cleared away many of their rivals, leaving dinosaurs free to expand into forms that would define the Jurassic and Cretaceous. The first dinosaurs remind us that greatness often begins quietly. They were not the largest, nor the strongest, nor even the most numerous. They were simply well suited to a changing world, flexible where others were rigid, efficient where others were clumsy. Their early steps across Pangea's soils may have seemed unremarkable, but in those steps lay the promise of future empires. The rustle of a Plateosaurus herd, the dash of a Coelophysis pack, the flutter of a pterosaur's wing. These were the sounds of possibility, carried across landscapes that were still raw from catastrophe, but alive with renewal. And, as the Triassic rolled onward, the role of dinosaurs would grow, their presence spreading into every corner of the supercontinent, until the world itself began to shift under their feet. When we think about Earth, it feels steady and familiar, as though the length of a day has always been the same. But in the age of Pangea, the rhythm of time itself was different. The planet spun a little faster on its axis, and because of this, days were shorter than the ones we live through now. Instead of 24 hours, a full rotation might have lasted only about 22. The difference sounds small, but over millions of years, it shaped everything from winds to tides to the cycles of life. Imagine waking in that world and noticing that dawn arrived sooner than expected, that the sun slipped west more quickly, that night returned before you were ready. For creatures adapted to Pangea's climate, that pace was normal. For us, it would feel like the planet had picked up speed beneath our feet. The reason behind these shorter days lies in a slow dance between Earth and its moon. When the moon first formed billions of years ago, the Earth spun much faster. Days may have lasted only a few hours. Over time, the moon's gravity has been pulling on our oceans, creating tides. With each tide, energy is transferred from Earth to the moon, pushing the moon slightly farther away while slowing Earth's rotation. This process continues even now, which is why our days are gradually lengthening. But 200 million years ago, when Pangea stretched across the surface, the moon was closer, and the planet's spin still quicker. Life on Earth grew within that tempo. Plants opening their leaves to shorter bursts of light, animals moving within cycles of day and night that flowed more swiftly than ours. If you picture a Triassic plain under the sun, you might notice how shadows shifted a little faster across the ground. A herd of Plateosaurus feeding among conifers would experience morning and evening compressed into a tighter span, though of course they would not know it. For nocturnal creatures, the hours of darkness were briefer, demanding efficient activity before light returned. Frogs calling near rivers had less time to sing. Insects humming through the night air had less time to feed. Yet nature adjusted, as it always does. The sky itself also looked different. Without human settlements, without artificial light of any kind, night was pure. Stars burned with an intensity that is almost impossible for us to imagine today. Even in deserts far from cities, our modern view is dulled by faint glows of electricity scattered across the globe. On Pangea, darkness was total, and in that darkness the heavens blazed. The Milky Way arched in sharp clarity, thousands upon thousands of points of light pressing against the black. The moon appeared larger because it was closer, pulling the tides of Panthalassa with greater force. Its glow painted silver paths across rivers and lakes, guiding nocturnal animals in their movements. A coelophysis looking upward might see more stars than we can count, but for that animal, the sky was not an abstraction. It was simply part of the background of life. For us, though, to imagine such a sky is to remember a kind of grandeur now mostly hidden. The shorter day also meant winds behaved differently. With a quicker spin, Earth's atmosphere was stirred in more energetic patterns. Jet streams, those fast rivers of air high above the surface, shifted with greater speed, redistributing heat in distinctive ways. Monsoons sweeping across Pangea may have been more intense, their timing influenced by the rhythm of the rotating globe. Coastal storms rolling in from Panthalassa may have carried a sharper edge, guided by the slightly different balance of forces. For plants rooted in the soil, this mattered because rainfall was never predictable. For animals, it meant migrations and movements had to remain flexible. The link between time and life was constant, even if invisible. Another subtle difference comes from how tides responded. With the moon closer and Earth spinning faster, tides along Pangea's coastlines may have been more dramatic, rising and falling with force. Estuaries and tidal flats would have pulsed with energy, creating feeding grounds rich in nutrients. For small reptiles hunting along the shore, these cycles determined when food was easiest to find. For marine creatures in the shallows, the rhythm of tides structured their entire existence. In this way, the length of a day, something we rarely think about, was directly woven into survival. If we could stand in that time, watching the sun arc overhead, we might feel slightly unsettled by the pace. Afternoon would arrive earlier, evening would come before we expected. Yet as night deepened, the brilliance of the sky would hold us still. The absence of human light meant that even faint stars, invisible to us now, would shine. Constellations we know today, Orion, Scorpio, Cygnus, were there, though shifted by the slow wobble of Earth's axis, glowing over a world where dinosaurs were only beginning and mammals were still tiny shadows in the undergrowth. Some scientists suggest that higher light levels during shorter days could have influenced photosynthesis. Plants on Pangea's surface, from tall conifers to spreading cycads, absorbed sunlight in bursts that were slightly briefer but more frequent. The constant cycle of day and night may have shaped growth patterns in ways we still do not fully understand. What we do know is that forests flourished, deserts expanded and contracted, and ecosystems adapted to the tempo of the planet itself. Even the color of the sky by day may have seemed sharper, clearer. With no haze of industry, no trails of aeroplanes, the blue stretched unbroken from horizon to horizon. Clouds drifted in pure whiteness, storms stacked themselves into towering forms over the vast continent. At sunrise and sunset, the air may have glowed with deeper reds and purples than most of us ever see, the scattering of light untainted by pollution. For early flying reptiles, those pterosaurs gliding above river valleys, the sky was both a stage and a refuge. Their wings outlined against a backdrop of colors more intense than modern skies can produce. Consider also the soundscape of that world. With days shorter, temperature changes between day and night could be sharper in certain regions. As evening fell, the cooling air might have carried sound differently, allowing calls of animals to travel farther. Frogs at the edge of a swamp could fill the darkness with their voices, while insects pulsed in rhythm until dawn returned sooner than expected. The cycle of activity was tuned to the swift turning of the earth, each creature fitting itself to the heartbeat of the planet. What makes this all the more extraordinary is that the difference between their world and ours is measured in minutes. 2 hours shorter in a day seems trivial, yet multiplied by millions of rotations, it reshaped the environment. It reminds us that even slight changes in planetary motion can ripple through climate, ecosystems, and the very perception of life. For us, it is a curiosity. For them, it was the only reality they knew. In reflecting on these faster days and brighter skies, we glimpse a world both familiar and alien. The land was the same earth we walk upon, the oceans the same waters, the stars the same galaxies, yet everything was framed by a rhythm just beyond our experience. To imagine it is to be reminded that Earth is not static. It changes constantly, slowly stretching days, shifting climates, redrawing maps. In the Triassic, under the united expanse of Pangea, Life carried on beneath a sky of brilliance and a sun that moved more quickly across the heavens. The forests grew, the rivers carved, the animals fed and hunted, all under a tempo that has since eased but never ceased. And as the days turned, one after another, the planet prepared for changes still to come, carving the pathways that would lead into the landscapes of the Jurassic, where rivers would deepen, floodplains would expand, and the story of life would continue in new and vibrant forms. Across the heart of what is now the American Southwest lies a geological story written in bold color. Layers of deep crimson, ochre, purple, and gray stretch across cliffs and badlands, silent but vivid reminders of a world long gone. This is the Chinle Formation, a vast record of Triassic landscapes that once spread across Pangea, where great rivers meandered, floodplains opened wide, and forests grew, only to be buried and turned into stone. To walk through these rocks today is to move across time itself, into an age when the land was alive with early dinosaurs, crocodile-like predators, amphibians, and forests so dense that their remains would one day harden into the petrified wood we marvel at now. In the Triassic, these regions were far from the deserts we see today. Instead, they were low-lying basins fed by immense rivers flowing from highlands far to the west. These rivers carried sand, mud, and silt, spreading them across wide floodplains. Each flood left behind new layers, building a landscape that was constantly shifting. Sometimes the rivers braided into many channels, weaving across each other in restless patterns. At other times, they gathered into single currents, carving deep banks before spilling outward again. With every change, they recorded their movements in sediments that hardened into the colorful rocks we see now. The reason those rocks glow red comes from iron within them. When iron minerals in the sediments were exposed to oxygen, they rusted, turning shades of red and orange. This process happened over and over as floods brought new material and seasons shifted the chemistry of the soil. The result is a palette of color that paints entire valleys, so striking that it looks almost otherworldly. But in the Triassic, it was not a land of silence and stone. It was alive with water, plants, and animals adapting to the flood cycles. Along the banks of these rivers grew dense forests. Conifers stretched upward, cycads clustered in thickets, and ginkgo trees spread their fans of leaves. Beneath them lay ferns and horsetails, filling the undergrowth. These forests thrived in the wet soil near streams, but they also faced danger. When floods came, trees could be uprooted, carried downstream, and buried in sand and mud. Over millions of years, some of these buried trunks absorbed minerals from groundwater, turning cell by cell into stone. This is how the great petrified forests of the Chinle Formation formed. Today, in places like Petrified Forest National Park, entire logs lie scattered across the land, glittering with quartz crystals, their colors ranging from purple to green to white. They are silent witnesses, fossilized forests that preserve the memory of Triassic ecosystems. The rivers themselves were lifelines for animals. Amphibians lurked in the water, some growing to enormous sizes. Crocodile-like reptiles known as phytosaurs patrolled the banks, their long jaws lined with teeth, waiting for prey to draw near. Their eyes and nostrils were set high on their heads, allowing them to float almost invisible at the surface, much like modern crocodiles. Early dinosaurs, including Coauthysis, darted among the floodplains, quick hunters chasing smaller reptiles and insects. Larger plant eaters like Platosaurus wandered the forests, stripping leaves as they moved in herds. The Chinle was a crossroads of life, a place where ecosystems overlapped in constant interaction. One of the most remarkable aspects of the Chinle Formation is the abundance of fossils it holds. Skeletons of amphibians, reptiles, and early dinosaurs are preserved in its layers, often alongside the petrified trees that once shaded them. Trackways show where animals walked across mud flats, their prints later filled with sand and hardened into stone. Even delicate impressions of plants remain, capturing the shapes of leaves that fell into the sediment millions of years ago. These fossils tell us not only who lived here, but how they lived. For instance, the abundance of phytosaur remains shows they were dominant predators of the rivers. The presence of early dinosaurs in groups suggests they may have hunted together or at least shared territories. Fossilized logs reveal that forests were not sparse patches but thick woodlands capable of supporting large plant-eating reptiles. Each clue adds to the picture of a land far more vibrant than its rocky remains suggest. Imagine standing on a Triassic floodplain within the Chinle. The air is warm, the ground moist from recent rains. A river winds lazily nearby, its water carrying the reddish tint of suspended sediments. Forests line the banks, their leaves rustling in the breeze. From the shadows, a phytosaur slips silently into the current, only its eyes breaking the surface. Overhead, a small pterosaur glides, its wings catching thermals rising from the warm land. In the distance, a herd of Plateosaurus browses, their long necks swaying as they reach into the trees. Suddenly, a flash of movement. Several Swelophyses dart across the open ground, chasing lizards through the undergrowth. Life pulses through every corner of the landscape, vibrant, yet always at the mercy of the rivers that shape it. Floods were both destructive and life-giving. When waters surged, they could wipe out forests and scatter animals, but as the waters retreated, they left behind fertile soil. New plants sprouted quickly, attracting herbivores, which in turn drew carnivores. This constant cycle of destruction and renewal gave the Chinle its rhythm. It was a land that never stood still, always remade by water. Over time, the layers built up into hundreds of meters of sediment. Each band of color marks a different chapter of the Triassic. Pale green layers represent ancient swamps. Bright red layers mark well-oxygenated soils. Purples and grays show chemical changes from shifting groundwater. To a geologist, these colors are not just beautiful, they are a code, a record of climate shifts, floods, and droughts spanning millions of years. To a storyteller, they are the palette of Earth itself, painting history in stone. The petrified forests hold another secret. In the minerals that replaced the wood, tiny details of the original trees remain. Growth rings show how seasons changed. Patterns of cells reveal the structure of bark and leaves. Even fungi that lived within the wood are sometimes preserved, offering a glimpse into microscopic life that shared the forests. To see these details under a microscope is to look directly into a moment of the Triassic, frozen forever in crystal. Beyond their beauty, the Chinle deposits tell us how ecosystems recovered after the Great Dying. By the time these rivers flowed, life had rebounded. Forests were strong, animal populations diverse. Though extinction still loomed in the future, in this slice of time the earth was rich again. The rivers carried not only water and sediment but resilience, the evidence that life could rise after collapse. Standing in the Chinle today, surrounded by petrified logs and cliffs of red stone, it is difficult to imagine the vibrancy that once filled the land. Yet if you close your eyes, you can almost hear it. The rush of rivers, the creak of trees in the wind, the calls of amphibians from shaded pools, the splash of a predator entering the water. The colors around you become more than rock. They become echoes of motion, of cycles that never ceased. The Chinle reminds us that landscapes are not static. What is desert now was once a living floodplain. What is stone now was once wood, soft and green. What seems silent now once rang with calls and footsteps. By reading its layers, we reconnect with that ancient vitality, seeing how rivers shape not only land but life itself. And as those rivers wound across Pangea, they were part of a larger system, connected to seas and valleys beyond. The story of water did not end at the floodplain. It carried on, carving new paths, feeding new forests, and eventually joining with the ocean that still surrounded the supercontinent. While Panthalassa stretched like an endless ring around Pangea, there was another body of water carving its own quiet story inside the supercontinent's embrace. This was the Tethys Ocean, a sea that both connected and divided, closing in one region even as it opened in another. It was not a vast encircling world sea, but a ribbon of blue winding between land masses, shaping climates, guiding currents, and creating environments where marine life flourished in remarkable form. To understand the Tethys, imagine Pangea not as a featureless mass of stone, but as a puzzle of continental blocks slowly grinding and shifting against one another. In the east, what would one day become Asia pushed and folded against other fragments. In the west, land drifted apart. Between them, the Tethys expanded. like a breath being drawn in, its waters flowing into new spaces created by the slow pulling of the Earth's crust. At the same time, in other places, sections of the Tethys were closing, squeezed shut by colliding continents. It was a sea forever caught between opening and closing, retreat and advance, yet always alive, with the creatures that found a home within its depths. Along its shores, the landscape was unlike the harsh deserts of Pangea's deep interior. Here, warm breezes carried moisture inland, forests grew in richer belts, and wetlands lined river mouths. But it was in the sea itself that the greatest variety lived. The shallow margins of the Tethys hosted reefs, built by corals and sponges. Their structures rose from the seabed, creating havens for fish, mollusks, and crustaceans. Ammonites, those coil-shelled relatives of squid, drifted through its waters, their shells catching sunlight as they moved in gentle spirals. Some were as small as coins, others as large as cartwheels, each chambered shell a precise construction that balanced buoyancy and grace. These creatures thrived in the nutrient-rich waters where rivers emptied into the sea, drawing life into dense webs of interaction. The deeper zones of the Tethys told another story. Here swam ichthyosaurs and nothosaurs, sleek marine reptiles that hunted with precision. Their bodies cut through the water like living arrows, their movements silent but deadly. They chased schools of fish, pursued ammonites, and filled the role of apex predators in marine ecosystems. For them, the Tethys was both highway and hunting ground, stretching far enough to allow migration, yet always framed by the continental margins that defined its limits. What made the Tethys unique was not only the life it supported, but the way it shaped Earth's systems. As continents shifted, the size and shape of the sea changed, altering global currents. Warm waters flowed through its basins, redistributing heat across Pangea. Storms built strength as they crossed its surface, carrying rains inland to regions that would otherwise have remained dry. In this way, the Tethys was more than a body of water. It was a force that influenced climate across an entire hemisphere. The edges of the Tethys were dynamic. Coral reefs rose and fell with sea levels, sometimes thriving, sometimes buried beneath shifting sediments. Lagoons formed behind barrier reefs, their calm waters filled with delicate light. Estuaries teemed with activity as freshwater rivers met the salty sea. The mixing of waters created nutrient surges, feeding plankton blooms that in turn supported fish and reptiles. It was a cycle of abundance, where every shift in tide or current had ripple effects across the food chain. Fossils from ancient Tethyan deposits reveal the variety of life that lived there. Fish with armored scales, delicate starfish, brachiopods anchored to the seabed, and marine reptiles preserved in remarkable detail all tell of a sea bustling with activity. Some regions became rich fossil beds because sudden events, such as underwater landslides or volcanic ashfalls, buried entire communities at once, freezing them in time. From these sites we learn not only about individual species but about entire ecosystems, preserved as though they had been pressed between pages of stone. On land, the Tethys shaped coastlines that were gateways for migration. Animals that lived along its edges encountered environments unlike the dry heart of Pangea. Here, rainfall was more reliable, vegetation denser, and food more abundant. For dinosaurs and other reptiles, coastal regions of the Tethys offered havens where survival was easier, and from which species could spread into new territories. It was in these shifting zones between sea and land that evolutionary experiments often flourished, producing forms that might not have survived in harsher interiors. The Tethys also left behind a lasting imprint on geology. Many of today's mountain ranges, including parts of the Alps and the Himalayas, owe their origin to the Tethys. As continents eventually pressed together, sections of its seabed were thrust upward, carrying with them marine fossils that now rest on peaks thousands of meters above sea level. To hold a seashell in the high Himalayas is to touch a fragment of the Tethys, proof that this vanished ocean once covered places now far from any shore. Imagine standing on the Triassic coast of the Tethys. The air is humid, the sky filled with drifting clouds. Before you, a reef glows with life. Corals spreading their delicate arms, fish darting in flashes of color. Beyond the shallows, the water darkens into deeper blues, where the shadow of a nothosaur passes silently beneath the waves. Overhead, a pterosaur glides, circling above the shoreline before diving for an unwary fish. The sound of the surf mingles with the calls of creatures from the forest edge. It is a scene of motion, of connection between land and sea, of a world balanced on the edge of transformation. The importance of the tethys lies not only in its role during Pangea's existence, but also in its legacy. Long after the supercontinent broke apart, the remnants of the tethys continued to shape new oceans. The Mediterranean, the Black Sea, all trace their origins to fragments of this ancient body of water. The story of the tethys did not end with Pangea. It echoes into the present, hidden in coastlines and seabeds that still carry its mark. For the creatures that lived then, the tethys was simply home. For ammonites, it was a realm of drifting, feeding, and multiplying. For ichthyosaurs, it was a hunting ground. For corals, it was a place of growth, polyps stacking upon polyps until entire reefs stretched for kilometers. For countless smaller organisms, it was the only world they knew, and together they made the tethys one of the richest and most influential seas of its time. To think of the tethys is to imagine both presence and absence, a sea that once stretched wide, but now exists only in fragments. Its waters have long drained away, but its story is written in rocks, in mountains, in fossils carried upward from depths that no longer exist. The sea that split the land is gone, but its memory endures, shaping our understanding of Earth's shifting surface. And just as the tethys once opened and closed, carving paths for marine life, so too would the land of Pangea itself begin to fracture, leaving behind valleys where lakes formed, and footprints pressed into soft mud told the story of animals passing through, unaware that they were walking at the edge of an ocean, being born. The supercontinent of Pangea looked solid from above, an unbroken sweep of land wrapped by the endless waters of Panthalassa. But deep within its crust, changes were already stirring. Tectonic forces never sleep, and by the late Triassic, the same power that had welded continents together was beginning to pull them apart. Along long valleys, the surface cracked and sagged, creating depressions that filled with water. These were the rift valleys, the first signs of a new ocean trying to be born. To walk through these landscapes then would have been to see Earth in transition, a world where stillness was only an illusion. The valleys stretched for hundreds of kilometers, bordered by cliffs of fresh rock. Fault lines cut across the ground where pieces of land slid past one another. In the lowest parts, rainfall and rivers collected, forming lakes that shimmered under the sun. These lakes were not small pools, but enormous bodies of water, sometimes stretching across entire regions, their surfaces alive with reflections of the sky and the forests around them. The water levels rose and fell with the seasons, and with each change, sediments layered the basins. Fine mud settled at the bottom, preserving traces of whatever touched it. Fish left faint impressions of their fins, insects fell upon the water and were entombed in silt, and most enduring of all, dinosaurs pressed their feet into the wet shores, leaving prints that hardened into stone. These footprints are among the most haunting records of the Triassic. In places like the Connecticut River Valley in North America, slabs of red sandstone still carry the tracks of animals that passed more than 200 million years ago. Some prints are delicate, showing 3 slender toes pressed sharply into mud. Others are massive, deep enough to suggest creatures of great size and strength. Walking across those ancient shorelines, you would have seen herds of early dinosaurs pausing to drink, their young moving alongside them, their tracks weaving together into patterns of daily life. Telephyses, small and agile, left narrow trails as they hunted along the margins. Larger prosopods, ancestors of giants yet to come, pressed wider impressions as they fed on vegetation nearby. Each print was a mark of motion, of presence, of living animals in a landscape now silent. The lakes of the rift valleys were dynamic environments. Seasonal rains could swell them into wide expanses, while dry intervals shrank them into shallow pans. These fluctuations created zones of mudflats and shifting shorelines, where plants and animals adapted to constant change. Reeds and horsetails grew in the shallows, stabilizing the banks. Fish darted through the waters, some leaving behind entire schools fossilized together when sudden drops in oxygen suffocated them. Amphibians lingered near the edges, their calls echoing across the valleys at dusk. For predators, these lakes were hunting grounds. Phytosaurs with their crocodile-like forms slid into the waters, lurking just below the surface. Dinosaurs approached cautiously, aware of dangers hidden in the stillness. Yet life returned again and again, because water was precious, and the valleys offered it even when the interior of Pangea lay under drought. The geology of the rift valleys tells us how the Atlantic Ocean was beginning to form. As the land stretched, the crust thinned, allowing magma from below to rise. In some places, lava flowed across the ground, cooling into dark basalt that still caps cliffs today. In others, the stretching created faults that dropped sections of crust, forming deep basins. These basins collected sediments and water, becoming lakes that could last for thousands of years before shifting again. Over time, the cracks widened, though not yet enough to open a true ocean. It was as though the Earth was rehearsing for a future separation, testing the strength of its seams. The fossils of these valleys are remarkable not only for their abundance, but for their detail. Whole fish are preserved in thin layers of shale, their scales still shimmering under the right light. Insects appear with wings spread, trapped in fine mud. Leaves pressed into the sediments retain the outlines of their veins. Most striking of all are the trackways, lines of footprints stretching across slabs of stone, showing not just single moments, but journeys. A trail of small theropods might curve and then pause, as though the animal turned its head or stopped to rest. Larger prints follow, sometimes overlapping, recording interactions we can only guess at. These tracks are more than fossils. They are stories of movement, a diary written in mud and sealed by time. Imagine one of these lakes on a warm Triassic afternoon. The water ripples in the wind, glinting under a bright sun. Along the shore, reeds sway, and dragonflies with wingspans wider than your hand skim above the surface. A group of small dinosaurs approaches, their feet sinking slightly into the soft ground as they drink. Behind them, a larger prosauropod steps carefully, its weight leaving deep impressions. Across the water, a phytosaur slides silently into view, only its nostrils breaking the surface. In the distance, smoke curls from a fissure where magma has broken through, a reminder that the land itself is unsettled. It is a landscape of beauty and tension, of life flourishing on ground that is slowly tearing apart. The importance of the rift valleys lies not only in their biology but also in their role in Earth's history. They are the first hints of the Atlantic, the great ocean that would one day divide the Americas from Europe and Africa. In the Triassic, that division was only beginning. The valleys were like stitches pulling apart in slow motion, each crack another step toward separation. When we look at them now, preserved in layers of sandstone and basalt, we see the opening chapters of a story that continues into our own time. Today, the Atlantic still widens by a few centimeters each year, the echo of those first ruptures long ago. The lakes of the rift valleys also played a role in preserving climates. Their surfaces reflected sunlight, their waters moderated local temperatures, and their evaporation fed clouds that brought rain back to the land. In this way, they were stabilizers in a changing world, small yet significant influences on the rhythm of life. Animals gathered here not only for water, but for the ecosystems the lakes supported: plants, insects, fish, and prey. In their gatherings, they left the tracks that became one of the richest records of the Triassic. The footprints themselves have fascinated scientists for centuries. When first discovered in the 19th century, they were sometimes mistaken for the marks of giant birds. It was only later that paleontologists understood they belonged to early dinosaurs and other reptiles. Today, they are studied with precision, each angle and depth measured to reveal the size, speed, and even behavior of the animals that made them. Some tracks show running, with toes digging deep into the mud. Others show careful walking, with prints evenly spaced. Together they form a chorus of movement across a vanished landscape. Beyond the tracks, the rift valleys hold another kind of story. The story of Earth's restlessness. These valleys remind us that continents are never still. What feels solid under our feet is always drifting, colliding, or stretching. In the Triassic, that motion was tearing Pangea at its seams, and the rift valleys were the visible scars. Lakes filled them temporarily, forests grew around them, animals left their marks, but the valleys themselves were only temporary. Eventually, the stretching would succeed, the land would split, and seawater would pour in, turning valleys into the first inlets of the Atlantic. Yet before that happened, life thrived in the shifting spaces, adapting to the cycles of flood and drought, eruption and calm. To picture the rift valleys now is to imagine a place of contrasts, tranquil lakes set within landscapes of fire and fault lines, delicate footprints pressed into mud that lay beside cracks glowing with molten rock, forests swaying beside waters that might vanish in the next season. It was a world of transition, poised between unity and division, and through it all, animals carried on, leaving behind the quiet evidence of their passing. When we hold a slab of sandstone marked with three-toed prints, we hold more than stone. We hold a moment when a dinosaur lifted its foot, unaware that the impression would last for over 200 million years. We hold a fragment of Earth's great story of separation, of oceans being born from rifts in the land. And as we trace those prints with our fingers, we see how even the smallest step can become eternal when recorded by the patience of geology. The rift valleys, with their lakes and tracks, were the beginning of a new chapter for Earth, one that would carry forward into eruptions and extinctions, and finally into the full opening of the Atlantic Ocean, reshaping the world forever. Beneath the surface of Pangea, pressure was building. For millions of years, the supercontinent had rested like a giant sealed lid over Earth's interior heat. But nothing beneath our planet ever stays quiet forever. As the Triassic drew toward its end, cracks that had once been narrow rift valleys deepened, and from those wounds in the crust came fire on a scale beyond anything humanity has ever witnessed. This event is known today as the Central Atlantic Magmatic Province, or CAMP, one of the largest volcanic outpourings in Earth's history. To imagine it, picture fountains of molten rock shooting into the sky, rivers of lava spreading for hundreds of kilometers, and ash clouds so immense they dimmed the sun across continents. It was not a single eruption, but pulses of activity, repeated over hundreds of thousands of years. Each pulse released more lava than all modern volcanoes combined might produce in centuries. The sheer volume is staggering. Estimates suggest that lava covered an area of nearly 11 million square kilometers, roughly the size of the entire United States and Canada put together. Whole regions that would later become parts of Africa, North America, South America, and Europe were drowned under sheets of basalt, layer upon layer, until the land itself was reshaped. But lava was only part of the story. When molten rock intruded into sediments rich in carbon and sulfur, it released enormous amounts of gases. Carbon dioxide flooded the atmosphere, driving rapid warming. Sulfur dioxide created acid rains that poisoned soils and waters. Ash darkened the sky, cooling the surface in the short term, only for greenhouse gases to trap heat for the long term. The climate swung wildly between extremes, leaving ecosystems struggling to keep pace. Forests withered, rivers turned toxic, and oceans became unstable. Marine life was especially vulnerable. As carbon dioxide rose, much of it dissolved into the seas, forming carbonic acid. This acidification stripped away the ability of corals and shell-forming creatures to build their skeletons. At the same time, warmer waters held less oxygen. Vast zones of the ocean became suffocating, forcing fish, ammonites, and marine reptiles into shrinking habitable regions. Fossil evidence shows a sudden crash in diversity at this time, entire groups vanishing from the record. On land, the story was no less dramatic. Many lineages of reptiles that had flourished through the Triassic disappeared. Whole families of large herbivores and predators alike were lost, yet not all perished. Dinosaurs, still relatively small and diverse in form, managed to endure and eventually expand into the niches left behind. The end Triassic extinction, triggered by the CAMP eruptions, cleared the stage for the Jurassic, when dinosaurs would rise to dominance. To grasp the human scale of such eruptions is nearly impossible. A single lava flow might have stretched across landscapes larger than some modern nations. Imagine standing near the edge of one. The ground trembles under your feet. A roar like thunder rolls continuously from the fissures as lava fountains reach hundreds of meters high. The air is thick with ash, the sky a murky red, the sun only a dim disk. Rivers of molten rock spread outward, their surfaces cooling to black even as glowing currents pulse beneath. Trees burst into flames from the heat alone, long before the lava reaches them. Animals flee in confusion, some trapped, some escaping, only to face barren lands in the aftermath. This was not a day or a week of catastrophe, but centuries of it. Wave after wave, across hundreds of thousands of years. Between eruptions, life would attempt to return. Plants sprouted in fresh soils, animals reoccupied valleys. But before ecosystems could fully stabilize, another eruption would come, resetting the cycle of destruction. Over time, the cumulative effect was too great. Entire food webs collapsed. In some places, fossil layers show abrupt breaks. Rich communities below, followed by silence above, only slowly filled again by survivors. Yet within this devastation lies one of Earth's paradoxes. Such immense destruction also set the stage for renewal. The basalt flows themselves, once cooled, became fertile ground for new vegetation. Volcanic ash added minerals to the soil, and by eliminating competitors, the extinction opened opportunities for groups that had been minor players. Dinosaurs, early mammals, and new forms of marine reptiles all expanded in the wake of crisis. The scars of the camp eruptions are still visible today. Across Morocco, eastern North America, Brazil, and even parts of Europe, layers of dark basalt lie exposed in cliffs and valleys. These are the remnants of that global outpouring, silent stone, witnesses to firestorms that once shook the earth. Geologists read them like pages in a book, each flow recording another surge of molten rock, another chapter of upheaval. Chemical fingerprints in the rocks match across continents, proof that these distant lands were once joined and shared the same volcanic convulsions. Scientists study tiny crystals within the basalts to determine the timing of eruptions, matching them with evidence of extinction in the fossil record. The alignment is clear. As the eruptions peaked, life faltered. The end Triassic extinction ranks among the big 5 mass extinctions in Earth's history, a turning point written both in stone and in the sudden absence of many creatures. Imagine again the world as it must have felt to those who lived through it. Skies darkened not just for days but for seasons. Rain fell, acidic, stripping leaves from trees and killing fish in lakes. Temperatures spiked, then dropped, then spiked again, as gases and particles played tug-of-war with the climate. Entire generations of animals faced unfamiliar and hostile conditions. Species that relied on narrow ranges of temperature or food sources simply could not adapt quickly enough. The fossil record goes silent for them, their last marks sealed in stone. Yet even in this chaos, resilience flickered. Ferns, hardy and fast-growing, often appear in abundance just above extinction layers, their spores filling the gaps left by fallen forests. These fern spikes mark nature's first attempts at recovery. Small dinosaurs, agile and adaptable, picked their way across barren floodplains, finding sustenance where larger competitors could not. In the seas, ammonites showed bursts of evolution, new forms appearing as survivors radiated into emptied niches. Life bent under pressure, but it did not break entirely. To consider the camp is to realize how interconnected Earth's systems are. Volcanism altered the atmosphere, which altered climate, which altered oceans, which altered life. Each pulse of lava echoed through the planet's web, leaving consequences far from its source. Even today, climate scientists study this ancient event as a warning. It shows how quickly massive injections of carbon can destabilize the world, how tipping points can cascade through air, water, and land. The difference now is that the source is not fissures of magma, but human industry. The lesson remains the same. The Earth responds, and often violently. Standing on one of those Triassic floodballs today, you might feel only solid rock beneath your feet. Yet beneath that quiet surface lies the memory of a world remade by fire. Every fracture in the stone, every mineral crystal carries a record of heat and eruption. To run your hand across the dark basalt is to touch a fragment of catastrophe turned to permanence. It is a reminder that Earth has burned before, and from that burning, life has reshaped itself. As Pangea continued to rift and the Atlantic slowly widened, the worst of the eruptions subsided, but the mark of that fiery interval remained, etched into both geology and biology. The dinosaurs that emerged afterward would stride into landscapes transformed by lava flows and climate shocks. Forests regrew on basaltic soils, new rivers carved through hardened rock, and ecosystems reorganized in patterns that would define the Jurassic. Fire across the Earth had swept away much of what was, but in its aftermath stood the beginnings of what was to come. In the wake of fire and ash, after lava had cooled into dark plains of stone and the air had begun to clear of choking gases, life returned to the world with a quiet determination. The end of the Triassic had stripped Earth of many of its creatures, yet the extinction was not a final silence. It was a pause, a clearing of the stage, and into that space came a new cast of characters ready to shape the landscapes of the Jurassic. Dinosaurs, once only one group among many reptiles, began to rise as the dominant animals of the land. Where the Triassic had been filled with competing lineages, phytosaurs, rausuchians, and other great predators, the extinction had narrowed the field. Those ancient forms were gone, leaving behind ecosystems with gaps waiting to be filled. Dinosaurs, small, nimble, and adaptable, stepped into those roles. They did not do so overnight. For millions of years, they lived alongside other survivors, gradually expanding as opportunities opened. But their bodies carried traits that gave them advantages. Upright postures allowed them to move efficiently, conserving energy as they roamed wide distances. Many could regulate their activity more effectively than their cold-blooded rivals, letting them survive temperature swings. Their varied diets meant some could thrive on tough plants, while others hunted prey across rivers and forests. Slowly, they multiplied and diversified, their footprints spreading across every corner of Pangea. In coastal lowlands, where the ground was rich and vegetation plentiful, herds of early sauropods gathered. These long-necked giants, descended from smaller ancestors of the Triassic, grew larger as new plants flourished on volcanic soils. Basaltic rock, once molten, now weathered into fertile ground that supported conifers, cycads, and ferns. With abundant food and fewer competitors, sauropods expanded into sizes never seen before. Their necks allowed them to sweep wide areas of forest for leaves, their bodies heavy but efficient in motion. Alongside them, early stegosaurs and ornithischians appeared, experimenting with body shapes that would one day define whole families of plant eaters. Predators followed. Where herbivores grew, carnivores adapted to hunt them. Theropods, once small and lightly built, developed new forms. Some grew larger, their jaws stronger, their teeth more special. Others remained fast and slender, hunting smaller prey or scavenging along floodplains. These hunters shaped the behavior of the herbivores, forcing them into herds, driving them toward forests or open spaces, depending on the threat. Every shift in predator strategy was answered by a shift in prey behavior, an endless dialogue written in tracks and fossils. In the seas, reefs returned after struggling through acidification and oxygen loss. With volcanic activity easing, waters grew more stable. Corals found new footholds, rebuilding the complex structures that supported countless species. These reefs, stretching along the margins of the Tatus Ocean, once again became havens of color and activity. Ammonites spiraled through the water in great numbers, their shells showing new patterns and forms. Fish diversified, filling niches left empty by the losses of the extinction. Marine reptiles, too, rebounded. Ichthyosaurs flourished in open waters, their sleek bodies chasing schools of fish across great distances. Plesiosaurs emerged with long necks and broad flippers, patrolling shallower seas and lagoons. The oceans, once suffocating, now teemed again with motion, proof of resilience woven into the fabric of life. On land, forests spread widely across the supercontinent. The basalt plains of the central Atlantic magmatic province broke down over time, their minerals feeding soils that encouraged growth. Ferns sprouted first, fast and opportunistic. Conifers rooted next, reaching upward with tall trunks and needle-like leaves that resisted drought. Cycads grew in clusters, their crowns of stiff fronds shading the ground below. Ginkgos, with their fan-shaped leaves, dotted the landscape. These forests were not the flowering jungles we know today, but they were dense, green, and alive. They stabilized soils, cooled the air, and provided shade and shelter for animals. The return of trees meant the return of layered habitats, branches for insects and small reptiles, trunks for climbing animals, and forest floors for larger creatures. Insects buzzed through the undergrowth, pollinating in ways different from modern flowers, feeding on spores and sap. Early mammals, tiny and nocturnal, darted in the shadows, living quiet lives under the feet of dinosaurs. They chewed on seeds, insects, and roots, their smallness a shield against predators. Though overshadowed by giants, their resilience would carry them forward into future ages. The ecosystems of Pangea stabilized, but they did so in new forms. Where once the Triassic had been a patchwork of many reptilian families, the Jurassic saw dinosaurs take the lead. Their rise rearranged food webs. Plants adapted to grazing and browsing pressures, developing tougher tissues. Dinosaurs in turn developed stronger jaws and new feeding strategies. The cycle of adaptation continued, but now under the guidance of these dominant animals. The very landscapes reflected their presence. Floodplains bore the trampling of herds. Forests opened where giants fed. Tracks pressed into mud, hardened into stone, leaving behind silent testaments of their movements. Even climate patterns shifted under the influence of spreading vegetation, as forests altered rainfall and winds carried spores across continents. The stabilization of life after the end Triassic extinction reveals a deep truth about Earth. Destruction is never the final word. Fire had scarred the planet, but from that scar, new possibilities emerged. The survivors carried with them traits that allowed expansion, and the emptiness left by vanished groups became space for innovation. This is how evolution works, not as a steady climb, but as a rhythm of collapse and renewal. Each wave of loss clears ground for what comes next. The map of life was rearranged, not erased. Standing in a Jurassic valley, you would have seen herds of sauropods moving slowly across open land, their long necks swaying like living towers. You would have heard the calls of smaller dinosaurs echoing from the trees. At night, insects hummed in the warm air while early mammals rustled unseen. Rivers meandered through broad floodplains, their waters reflecting stars unbroken by artificial light. In the seas beyond, reefs glowed with life, ammonites drifting in gentle spirals, ichthyosaurs surfacing for breath before plunging again into the depths. It was a world rebuilt, familiar yet transformed. The dominance of dinosaurs was not the only story. In the oceans, the return of reefs created biodiversity that rivaled anything on land. Corals layered themselves into towers and ridges, sponges filtered currents. Fish with new shapes and colors darted among crevices. Predators like plesiosaurs hunted with long, sweeping necks, snapping fish from schools with sudden precision. Ammonites exploded into new forms, their shells spiraling into tighter coils, ribbed with patterns that marked different species. Each adaptation was both a sign of survival and a preparation for future challenges. What makes this period remarkable is not only the variety of life, but its balance. For the first time since the great volcanic upheavals, ecosystems across Pangea found a rhythm. Forests stabilized the land. Rivers carried nutrients to the sea. Reefs filtered waters and sheltered fish. Dinosaurs filled niches from towering herbivores to swift predators. Even small mammals found stable places in the web of life. It was as if the planet, after centuries of convulsion, exhaled and settled into a calmer pace. The world was still restless beneath the crust, but on its surface, life thrived again. Scientists today trace this recovery through rocks and fossils. Layers above the basalt flows show renewed plant growth, indicated by coal deposits formed from dense vegetation. Dinosaur bones appear in greater abundance and diversity. Ammonite fossils multiply, each layer revealing new shapes. Even pollen grains preserved in sediments tell of expanding forests. The evidence is clear. After devastation, Earth had entered a phase of rebuilding, one that would set the stage for millions of years of dinosaur rule. The story of life rearranging the map is both literal and symbolic. Literally, continents continued to drift, shaping coastlines and seas. Symbolically, life itself redrew its own map, shifting dominance from one group to another, from lost Triassic reptiles to flourishing Jurassic dinosaurs. The reef systems expanded the map of marine ecosystems, creating pathways for diversity. Forests expanded the map of terrestrial life, spreading across volcanic soils. In every sense, the blueprint of the living world was revised, laying foundations for the future. The resilience shown then continues to resonate. It reminds us that while catastrophes can erase entire lineages, they also clear the ground for new growth. That pattern has repeated across ages, each extinction followed by renewal. After the flames of the Central Atlantic magmatic province, after the gases and suffocating seas, the world found its balance again. Dinosaurs grew into their age, reefs flourished once more, and ecosystems stabilized into a harmony that would endure until the next great upheaval. The Earth had rearranged itself, not only in stone, but in life. The age of Pangea eventually gave way to something new. The cracks that first appeared as quiet rift valleys widened until seas poured in, and over millions of years the single landmass separated into the continents we know today. Yet the memory of that united Earth did not vanish. It remains written into the rocks beneath our feet, into the mountains that still rise across landscapes, and into the fossils that tell us of creatures that once roamed without border. These traces are the echoes of a world that existed long before human history. Reminders that the planet we live on is never fixed, but always moving and reshaping. The mountains themselves are among the most enduring marks. Where continents once collided to form Pangea, their force thrust stone upward into ranges so high they rivaled the greatest peaks of our own time. Though millions of years of wind and rain have worn them down, the cores of those mountains remain. The Appalachians in North America, the Atlas Mountains in Africa, and parts of ranges scattered across Europe are all fragments of those ancient collisions. To look at them today is to see a softened landscape, but within their roots lie rocks that once stood as jagged ranges on the edge of the supercontinent. They are the physical scars of union, preserved long after the continents drifted apart. Fossils hold another kind of memory, one not of stone but of life. Across distant continents, the bones of identical creatures have been discovered, linking lands that are now oceans apart. The remains of Mesosaurus, a reptile that swam in fresh water, appear both in South America and in Africa. Glossopteris, an early plant with distinctive leaves, is found across lands that once formed the southern part of Pangea. These shared fossils were among the first clues that convinced scientists of continental drift, proof that what is now divided was once joined. To hold such a fossil is to touch the imprint of a world without boundaries, when rivers and forests stretched across a single land. Beyond fossils and mountains, there are subtler signs. The very shapes of continents are like puzzle pieces, their coastlines still echoing the moment they broke away. The bulge of Brazil fits against the curve of West Africa. The edges of North America align with those of Europe. These shapes are not coincidence, but the marks of separation, like fragments of a vase once whole. Even the sediments beneath the seas preserve layers of dust and minerals blown across the united continent, carried by winds that swept unbroken across thousands of kilometers. They are time capsules of a climate that belonged only to a world as vast and continuous as Pangea. What makes Pangea so compelling is not only its size, but its idea: one Earth, connected. For a time there were no continents standing apart, no seas dividing one land from another. Creatures could roam from what is now South America into Africa, from North America into Europe and Asia, without crossing oceans. Winds moved dust from deserts into forests a world away. Rivers carried sediments across regions that are today separated by vast seas. It was a vision of Earth whole, the planet at its most united. That unity, however, was always temporary. The same restless plates that built Pangea also prepared its undoing. Separation was not a sudden act, but a gradual widening, a rift becoming a valley becoming an inlet, an inlet widening into a sea. The Atlantic Ocean, which now stretches wider than the eye can follow, began as nothing more than a fracture in stone. Today it still grows by centimeters each year, a continuation of the motion that first split Pangea. To recognize this is to understand that our familiar map is only a moment in time. Millions of years from now, the continents will be arranged differently again, perhaps gathering into another supercontinent, perhaps drifting into new shapes altogether. Earth's map is never permanent. It is a canvas forever redrawn. And yet, though Pangea is gone, its influence endures in the very patterns of life that followed. The extinction that marked its late Triassic fires cleared the path for dinosaurs, whose reign stretched across the Jurassic and Cretaceous. The soils enriched by volcanic basalts supported forests that shaped ecosystems long after. Even the opening of the Atlantic carried consequences, creating new currents and climates that guided evolution in countless ways. In a sense, we still live in the world Pangea made, our landscapes and species shaped by its rise and fall. To stand on a modern coastline and look across an ocean is to see absence where there was once connection. Yet the memory of that connection is everywhere if you know where to look. It is in the matching rocks of distant lands. It is in the fossils of plants and reptiles that appear on both sides of oceans. It is in the folded strata of mountains that once rose from continental collisions. These are the echoes of one world, whispers from a time when the earth was simpler in shape but no less restless in spirit. The story of Pangea also invites reflection on the resilience of life. Through collision, fire, extinction, and separation, living things adapted. Some vanished, but others found ways to survive, to expand, to flourish in new conditions. Dinosaurs grew into giants, reefs rebuilt themselves, forests spread, mammals endured in the shadow. Each step in the planet's upheaval became a chance for renewal. That pattern has repeated across Earth's history, and continues still. Change is not the exception, but the rule. And Pangea is one of the clearest examples of how profound that change can be. For humans, the story carries another meaning. We live divided by oceans, our continents separated, but beneath those divisions is a shared origin. Once, all lands were one, all rivers connected, all skies swept by the same winds without interruption. The evidence lies beneath our feet in mountains and fossils, but the reminder runs deeper. The Earth itself is a single system, its pieces linked even when separated by seas. To remember Pangea is to remember that unity is as natural as division, and that both are temporary stages in the rhythm of the planet. Imagine, for a moment, the Earth of that time, a sunrise spreading across a single horizon, lighting deserts, forests, and mountains, all bound together. Herds of dinosaurs moving across floodplains, reefs bright beneath clear waters, winds carrying dust from red interiors into distant coasts. A world where distance meant only land, where oceans were borders on the outside rather than barriers within. That vision is gone. Yet in the quiet of rocks, in the patterns of continents, in the shared heritage of fossils, the echo remains. And so the memory of Pangea lingers, not just as a chapter of geology, but as a reminder of the Earth's restless creativity. The supercontinent may have broken apart, but its legacy is everywhere, sketched into landscapes, preserved in stone, and carried in the very arrangement of the continents we inhabit. One world, one land, long vanished but never forgotten, its presence still shaping the ground beneath us and the seas that surround us.